These are planets beyond our solar system that scientists have found orbiting in zones where liquid water could exist on their surfaces, and some of them share enough characteristics with Earth that researchers consider them potential refugees for humanity if we ever needed to leave our home world. The search for these worlds has consumed thousands of scientists across decades, cost billions of dollars, and produced discoveries that challenge everything we thought we knew about our place in the universe. Astronomers have confirmed more than 5,600 exoplanets as of today, worlds circling distant stars that range from scorching hot Jupiters to frozen super-Earths, and tucked among them are dozens that orbit in the habitable zones of their parent stars. The habitable zone, sometimes called the Goldilocks zone, marks the orbital distance where temperatures allow water to remain liquid rather than freezing solid or boiling away into steam. Water in its liquid form serves as the foundation for life as we understand it, acting as a solvent that enables the complex chemistry biological systems require. Finding Earth's twin has become more than just academic curiosity. The discovery would reshape how we view ourselves in the cosmic order and potentially provide insurance against extinction. Earth faces threats ranging from asteroid impacts to climate catastrophe to the eventual expansion of our Sun, which will render this planet uninhabitable in roughly 1 billion years regardless of any actions we take. Identifying another world capable of supporting human life gives our species options, even if reaching those distant shores remains beyond current technology. The planets we'll examine span distances from just over 4 light-years to more than 1,800 light-years from Earth, requiring journeys that would take millions of years at the speeds our fastest spacecraft currently achieve. Proxima Centauri b circles our nearest stellar neighbour and receives intense radiation that may have stripped away any atmosphere it once possessed. The TRAPPIST-1 system contains 7 Earth-sized worlds packed so tightly around their dim red star that 3 of them reside in the habitable zone, offering multiple chances for life but also presenting unique challenges. Kepler 452b orbits a Sun-like star at nearly the same distance Earth orbits our Sun, but that star burns older and hotter than ours, possibly cooking the planet into a Venus-like hellscape. Each of these worlds teaches us something different about what makes a planet suitable for life, from the importance of magnetic fields that shield surfaces from deadly radiation to the role plate tectonics play in regulating atmospheric carbon dioxide over geological timescales. The more we learn about Earth's uniqueness, the better we understand which features we should prioritize when evaluating distant candidates, and the clearer it becomes that habitability depends on far more than just orbital distance from a star. The techniques astronomers use to find these planets have evolved dramatically since the first confirmed exoplanet discovery around a Sun-like star in 1995, when Michel Mayor and Didier Queloz detected 51 Pegasi b using the radial velocity method. That initial detection launched a revolution in planetary science that continues accelerating today as more sophisticated instruments come online and analysis methods grow increasingly refined. Space telescopes like Kepler and TIAS have stared at hundreds of thousands of stars simultaneously, watching for the subtle dimming that occurs when a planet crosses between us and its host star. Ground-based observatories equipped with spectrographs have measured the wobble stars exhibit as their planet's gravity tugs them in tiny circles, revealing planetary masses and orbital parameters. Direct imaging systems on the largest telescopes have even captured actual photographs of a handful of massive young planets, glowing with the heat of their formation. These discoveries arrive at a moment when humanity's impact on Earth's climate and ecosystems has never been more apparent, lending urgency to questions about planetary habitability and the requirements for maintaining a life-supporting environment over millions of years. Understanding what makes other worlds habitable helps us appreciate the delicate balance that sustains life on this one, while simultaneously preparing us for a future where civilization might span multiple planets. The journey to find potentially habitable exoplanets combines cutting-edge technology with patient observation, sophisticated computer modeling with bold theoretical leaps, and the accumulated wisdom of multiple scientific disciplines from atmospheric physics to evolutionary biology. Every new discovery adds another piece to the puzzle of how common Earth-like worlds truly are in our galaxy, and whether we're alone in the universe or just one example among billions of life-bearing planets. What follows explores the most promising candidates for habitability that astronomers have identified, examining their characteristics in detail while also acknowledging the substantial uncertainties that remain about conditions on these distant worlds. We'll start by understanding how scientists detect planets light years away and determine whether they might support life, then examine specific examples that represent humanity's best current knowledge about where we might find Earth 2.0. The story of exoplanet discovery begins not with success, but with decades of frustration, false starts, and tantalizing hints that always dissolved under closer scrutiny. Astronomers theorized about planets orbiting distant stars for centuries, reasoning that if our Sun has planets, then other stars probably do as well. But detecting these worlds required technology and techniques that wouldn't exist until the late 20th century. Every claimed detection before the 1990s eventually proved to be instrumental error, stellar activity mistaken for planetary signals, or wishful thinking magnified by inadequate data. The first confirmed exoplanet discovery came in 1992 from an unexpected source, when astronomers Alexander Wolszczan and Dale Frail detected planets orbiting a pulsar designated PSR B25712. Pulsars are rapidly rotating neutron stars, the collapsed cores of massive stars that exploded as supernovae, and they emit beams of radio waves that sweep across space like cosmic lighthouses. The precise regularity of pulsar pulses allows astronomers to detect minute timing variations caused by orbiting planets, and Wolszczan and Frail found evidence for 3 worlds circling the dead star. These pulsar planets, while scientifically significant, didn't capture public imagination, because neutron stars represent stellar corpses rather than life-giving suns. The intense radiation environment around pulsars would sterilize any worlds orbiting them, and the planets probably formed from debris left over after the supernova explosion, rather than through normal planet formation processes. The astronomical community knew that finding planets around normal main-sequence stars like the Sun would represent the real breakthrough, demonstrating that planetary systems commonly form and persist around living stars. Michel Mayor and Didier Queloz achieved that breakthrough on October 6, 1995, when they announced the discovery of 51 Pegasi b using the LED spectrograph at the Haute-Provence Observatory in France. This planet orbited a Sun-like star just 50 light-years away, proving that Earth's solar system wasn't unique and that techniques existed to find planets around normal stars. The discovery earned Mayor and Queloz the Nobel Prize in Physics in 2019, recognizing how their work fundamentally changed astronomy and humanity's cosmic perspective. The planet they discovered shocked everyone because it defied all theoretical predictions about planetary system architecture. 51 Pegasi b, a gas giant planet with roughly half Jupiter's mass, orbited its star every 4.2 days at a distance of only 7 million kilometers. This hot Jupiter configuration made no sense according to planet formation theories developed from studying our solar system, where gas giants orbit far from the Sun, where temperatures allowed ice to condense and build massive planetary cores. The discovery of hot Jupiters forced planetary scientists to completely revise their models, introducing concepts like planetary migration, where worlds form at large distances then spiral inward through interactions with the protoplanetary disk or gravitational scattering by other planets. The paradigm shift demonstrated that our solar system's architecture, with small rocky planets close to the Sun and gas giants farther out, represents just one possible configuration rather than the universal standard. Planetary systems display remarkable diversity with hot Jupiters, super-Earths, mini-Neptunes, and orbital architectures unlike anything in our cosmic backyard. The radial velocity technique that discovered 51 Pegasi b measures the Doppler shift in a star's spectrum, caused by the gravitational pull of orbiting planets. As a planet orbits, both it and the star revolve around their common center of mass, causing the star to wobble in a small circle or ellipse. When the star moves toward Earth during its wobble, the wavelengths of emitted light compress slightly toward the blue end of the spectrum, and when it moves away, those wavelengths stretch toward the red. Measuring these wavelength shifts allows astronomers to detect the star's motion and calculate the planet's mass and orbital parameters. Early radial velocity surveys could detect stellar wobbles as small as 10 to 15 meters per second, precise enough to find hot Jupiters and other massive planets in close orbits, but insufficient for Earth-mass worlds at Earth-like distances. Each incremental improvement in spectrograph stability and calibration techniques pushed detection limits lower, enabling the discovery of progressively smaller planets in wider orbits. The HARP spectrograph, installed at the European Southern Observatory in 2003, achieved precision below 1 meter per second and discovered hundreds of exoplanets, including many super-Earths. The flood of exoplanet discoveries that followed 51 Pegasi b revealed that planetary systems are ubiquitous around Sun-like stars, with most hosting multiple planets rather than single worlds orbiting in isolation. Statistical analyses of radial velocity surveys found that roughly 50% of Sun-like stars have at least one planet, a figure that climbed toward 100% as survey sensitivity improved and could detect smaller planets. The galaxy contains hundreds of billions of planetary systems based on these statistics, providing countless potential sites where life might emerge. Ground-based transit surveys begun in the early 2000s demonstrated that photometric monitoring could detect planets when they passed between their stars and Earth, blocking a tiny fraction of starlight. The first exoplanet discovered through transits, Ogle TR56b, was announced in 2002 by the Optical Gravitational Lensing Experiment team. Transit surveys offered advantages over radial velocity measurements by revealing planetary sizes and allowing atmospheric characterization through transmission spectroscopy, though they required the fortuitous alignment of orbital planes with our line of sight. NASA's Kepler Space Telescope, launched in March 2009, revolutionized exoplanet science by conducting the first large-scale photometric transit survey from space. The spacecraft stared continuously at more than 150,000 stars in a patch of sky near the constellation Cygnus, measuring their brightness every 30 minutes for over 4 years. This unprecedented monitoring campaign detected thousands of planetary transits, revealing that small rocky planets are more common than gas giants, and that many stars host planets in their habitable zones. Kepler's prime mission ended in May 2013, when the second of 4 reaction wheels that kept the spacecraft precisely pointed failed, preventing the continuous monitoring that transit detection required. However, engineers developed a clever workaround using solar radiation pressure to stabilize the spacecraft, enabling the K2 extended mission that discovered hundreds of additional planets in different regions of the sky. Between its prime and extended missions, Kepler detected more than 4,000 planet candidates and confirmed over 2,700 exoplanets before its retirement in October 2018. The statistical revolution that Kepler enabled transformed exoplanet science from discovering individual worlds to understanding planetary populations. Researchers could now ask questions about how common different types of planets are, how planetary occurrence rates vary with stellar properties, and how planetary system architectures distribute across the galaxy. These population studies revealed that super-Earths and mini-Neptunes, planet sizes between Earth and Neptune that don't exist in our solar system, represent the most common planetary type around Sun-like stars. The Transiting Exoplanet Survey Satellite, or TESS, launched in April 2018 to continue Kepler's legacy, while focusing on bright nearby stars rather than distant targets. TESS scans nearly the entire sky in overlapping sectors, monitoring each region for about 27 days before moving to the next sector. This survey strategy prioritizes finding planets around the closest and brightest stars, because those systems allow the most detailed follow-up characterization with larger telescopes, enabling atmospheric studies and searches for biosignatures. Direct imaging of exoplanets represents the holy grail of exoplanet detection, because photographs provide unambiguous proof and allow detailed spectroscopic characterization without waiting for transits. The enormous brightness difference between stars and planets makes direct imaging extraordinarily challenging, requiring coronagraphs to block starlight and adaptive optic systems to correct for atmospheric distortion. The first directly imaged exoplanet, Tuamotu-Tulos 7b, was confirmed in 2005 orbiting a brown dwarf, followed by images of massive young planets around Sun-like stars in subsequent years. Ground-based observatories equipped with advanced adaptive optics and coronagraphs have directly imaged several dozen exoplanets, nearly all of them young massive worlds still glowing with the heat of their formation. These planets orbit at large distances from their stars where angular separation makes them easier to distinguish from stellar glare, typically beyond 10 or 20 astronomical units. Future extremely large telescopes will push direct imaging capabilities to smaller, cooler planets closer to their stars, potentially capturing photographs of true Earth analogues in the coming decades. Gravitational microlensing, where a foreground star's gravity focuses light from a background star and creates characteristic brightness patterns when planets alter the lensing effect, has discovered dozens of exoplanets, including some at Earth-like distances from their stars. This technique excels at finding planets at orbital distances where other methods struggle, but suffers from the limitation that lensing events are unique and non-repeating, preventing follow-up observations of the discovered planets in most cases. The technique surveys the galactic bulge where star density is highest, finding planets throughout the Milky Way rather than just in the Sun's immediate neighbourhood. The diversity of detection methods ensures comprehensive coverage of parameter space, with each technique sensitive to different types of planets and orbital configurations. Radial velocity excels at massive planets close to bright stars. Transits find small planets with short periods, direct imaging captures young massive planets at wide separations, and microlensing detects worlds at intermediate distances regardless of the host star's brightness. Combining results from multiple techniques provides a complete census of planetary populations and reveals the full range of planetary system architectures. The 25 years since 51 Pegasi B's discovery have completely transformed our understanding of planets and planetary systems, revealing that nature produces worlds in stunning variety, and that the architecture of our solar system represents just one possibility among countless alternatives: hot Jupiters, super-Earths, mini-Neptunes, circumbinary planets orbiting binary stars, free-floating rogue planets drifting through interstellar space, and bizarre worlds with diamond cores or water vapor atmospheres all exist in the exoplanet menagerie. This diversity emerged from thousands of individual discoveries by hundreds of astronomers using telescopes across the globe and in space, each detection adding another piece to the cosmic puzzle. Detecting a planet orbiting another star presents challenges that dwarf most observational problems in astronomy, mainly because planets produce no light of their own and remain tiny compared to the stars they orbit. Jupiter, the largest planet in our solar system, measures only 1/10 the diameter of the Sun despite being the second largest object orbiting it, and Earth's diameter spans less than 1% of our parent star's width. When you're trying to spot an Earth-sized world from light years away, you're essentially searching for a firefly next to a searchlight. The transit method, which has discovered the majority of known exoplanets, works by watching stars for the characteristic dimming that occurs when a planet passes between the star and Earth. When an exoplanet transits its host star from our perspective, it blocks a fraction of the starlight proportional to the planet's size relative to the star, and the dimming happens repeatedly with clockwork regularity as the planet completes each orbit. An Earth-sized planet transiting a Sun-like star causes the star's brightness to drop by roughly 80 parts per million, a change so subtle that ground-based telescopes struggled to detect it reliably until relatively recently. Kepler, launched in 2009, revolutionized exoplanet detection by staring continuously at more than 150,000 stars in a single patch of sky near the constellation Cygnus. The telescope measured stellar brightness every 30 minutes for over 4 years, accumulating enough data to detect multiple transits of planets, with orbital periods ranging from days to years. When the first of 4 reaction wheels that kept Kepler precisely aimed at its target stars failed in 2013, the primary mission ended, but the spacecraft had already detected thousands of planetary candidates that required years of follow-up observations to confirm. Scientists announced Kepler's discovery of the first near-Earth-sized planet in the habitable zone of a Sun-like star in July of 2015, when they revealed Kepler 452b to the world. That announcement came 20 years after the discovery of the first exoplanet around a main sequence star, marking 2 decades of progress from finding only massive hot Jupiters to identifying potentially rocky worlds in zones where liquid water might exist. The Kepler mission ultimately confirmed more than 2,700 exoplanets before its retirement, fundamentally changing our understanding of how common planetary systems are in the galaxy. The transit method works best for finding large planets with short orbital periods, because larger planets block more light, and planets on shorter orbits transit more frequently, providing more chances for detection. This creates an observational bias toward hot Jupiters and super-Earths orbiting close to their stars, while Earth-sized planets in year-long orbits around Sun-like stars remain among the hardest to find. Detecting such a planet requires observing at least 3 transits to confirm the periodic dimming pattern, meaning you need at least 3 years of continuous monitoring, plus additional time to rule out false positives caused by eclipsing binary stars or other astrophysical phenomena. Radial velocity measurements provide an independent method for finding exoplanets that doesn't require the fortuitous alignment of the orbital plane with our line of sight. When a planet orbits a star, both objects actually orbit their common centre of mass, causing the star to wobble in a small circle or ellipse. As the star moves toward Earth during its wobble, the wavelengths of light it emits get compressed slightly toward the blue end of the spectrum through the Doppler effect, and when it moves away from us, those wavelengths stretch toward the red. Measuring these minute wavelength shifts allows astronomers to detect the star's motion and infer the presence of orbiting planets. Current radial velocity instruments can detect stellar wobbles as small as 1 meter per second, precise enough to sense the influence of super-Earth planets in relatively close orbits around their stars. Earth causes the Sun to wobble at about 9 centimeters per second, which remains beyond the capabilities of existing spectrographs, but represents the target precision that next-generation instruments aim to achieve. The radial velocity method excels at determining planetary masses, since more massive planets induce larger stellar wobbles, complementing the transit method, which reveals planetary sizes from the amount of starlight blocked. HARPS, the high-accuracy radial velocity. Planet Searcher, located at the European Southern Observatory's La Silla facility in Chile, has discovered hundreds of exoplanets since beginning operations in 2003. This spectrograph achieves precision better than 1 meter per second by stabilizing the instrument's temperature to within 1,000th of a degree and carefully tracking wavelength calibration using thorium-argon lamps or laser frequency combs. The Espresso spectrograph, installed on ESO's Very Large Telescope in 2017, pushed precision even further, with the goal of reaching 10 centimeters per second and enabling the detection of true Earth analogues around Sun-like stars. Combining transit and radial velocity observations provides the most complete picture of an exoplanet's characteristics, with transit data revealing the planet's size and radial velocity measurements constraining its mass. These 2 parameters allow scientists to calculate the planet's density, which helps distinguish between rocky terrestrial worlds, icy planets, and gaseous giants. A planet with Earth's size but Neptune's mass would have a very low density, indicating a thick hydrogen-helium atmosphere, while a planet with Earth's size and mass would likely be rocky like our homeworld. The Transiting Exoplanet Survey Satellite, or TESS, launched in April of 2018 to scan nearly the entire sky for transiting planets around bright nearby stars. Unlike Kepler, which stared at one distant patch of sky, TESS observes each region of the sky for about 27 days before moving to the next sector, eventually covering 85% of the celestial sphere. This survey strategy prioritizes finding planets around the closest and brightest stars because those systems allow the most detailed follow-up characterization with larger telescopes. TESS has discovered over 400 confirmed exoplanets in its first few years of operation, including several worlds orbiting in their stars' habitable zones. TOI 700d, announced in January of 2020, became TESS's first Earth-sized planet discovered in a habitable zone, orbiting a small cool M-dwarf star about 100 light-years away. The abundance of M-dwarf stars, which make up roughly 75% of all stars in the Milky Way, means that finding habitable zone planets around these dim red stars could reveal billions of potentially life-supporting worlds throughout the galaxy. Direct imaging of exoplanets remains extraordinarily challenging because of the vast brightness difference between stars and planets, typically ranging from 1 million to 1 billion times fainter, depending on the planet's size and temperature. Coronagraphs and specialized adaptive optic systems can block the star's light while preserving faint signals from orbiting planets, allowing astronomers to capture actual photographs of a few dozen massive young planets still glowing with heat from their formation. These directly imaged planets orbit far from their stars, where the angular separation makes them easier to distinguish from stellar glare, and future instruments on extremely large ground-based telescopes will push direct imaging capabilities to smaller, cooler planets closer to their stars. The sheer number of exoplanets discovered since the mid-1990s has revealed that planetary systems are the rule rather than the exception around stars, with current estimates suggesting that on average, each star hosts at least one planet. Roughly 20% of Sun-like stars appear to have an Earth-sized planet in their habitable zones, based on statistical analyses of Kepler data, implying billions of potentially habitable worlds exist in our galaxy alone. Finding them requires patience and precision, but each discovery brings us closer to answering whether Earth-like conditions commonly lead to life, or whether our blue marble represents something truly special in the cosmic ocean. Liquid water's presence on a planetary surface serves as the primary criterion scientists use when evaluating habitability, not because life absolutely requires water, but because water-based chemistry represents the only form of life we know exists. Water's unique properties make it an exceptional solvent that can dissolve and transport the minerals and organic compounds living organisms need, while its high heat capacity helps moderate planetary climates, and its expansion, when freezing, prevents oceans from solidifying completely from the bottom up. The habitable zone concept defines orbital distances where planets receive enough stellar energy to maintain surface temperatures between water's freezing and boiling points, assuming reasonable atmospheric pressures. A planet orbiting too close to its star gets baked by intense radiation that evaporates any water into space, while a planet too far from its star freezes solid with water locked in ice that remains inaccessible to chemistry. The habitable zone's location and width depend on the star's size and temperature, with larger, hotter stars pushing their habitable zones farther out, while cooler, dimmer stars have habitable zones much closer in. Our Sun's habitable zone extends from roughly 9/10 of an astronomical unit, about where Venus orbits, out to perhaps 1.5 astronomical units beyond Earth's orbit. Venus likely receives too much solar energy for liquid water to exist on its surface, even if it had a thinner atmosphere, while Mars sits near the outer edge where water would remain liquid only with a much denser atmosphere than the thin carbon dioxide envelope it currently possesses. Earth resides comfortably in the middle of this habitable range, though our planet's actual surface temperature depends more on greenhouse gases in the atmosphere than on simple calculations of how much sunlight we receive. Red dwarf stars, the small, cool M-class stars that dominate the galaxy's stellar population, have habitable zones positioned very close to the star because of their relatively low luminosity. A planet in the habitable zone of a red dwarf might orbit at just a few million kilometers from its star, completing full revolutions in days or weeks rather than months or years. This proximity creates potential problems because tidal forces from the nearby star can lock the planet's rotation to match its orbital period, leaving one hemisphere in perpetual daylight, while the other side remains eternally dark. Tidal locking affects many exoplanets in habitable zones around M-dwarf stars, creating extreme temperature gradients between day and night sides that could prevent liquid water from existing in either location. Computer models suggest that thick atmospheres might transport heat from the hot day side to the frozen night side efficiently enough to create a ring of temperate conditions around the terminator line, separating light from dark, potentially allowing life to flourish in this permanent twilight zone. Whether such configurations actually support habitability remains an open question that future atmospheric observations should help resolve. Stellar activity poses another challenge for habitability around red dwarf star, which tend to produce powerful flares and emit intense ultraviolet and X-ray radiation, despite their relatively cool surface temperatures. These energetic outbursts can strip away planetary atmospheres over time through a process called photoevaporation, where high-energy photons break apart atmospheric molecules and give the resulting atoms enough energy to escape the planet's gravity. Proxima Centauri, our nearest stellar neighbour, unleashes flares with energies hundreds of times greater than Earth experiences from the Sun, bombarding any planets in its habitable zone with radiation that would challenge the survival of exposed organisms. A planet's mass influences habitability through multiple mechanisms, with more massive planets retaining thicker atmospheres and maintaining geological activity longer than smaller worlds. Earth's mass allows it to hold onto a substantial nitrogen-oxygen atmosphere at the correct pressure for liquid water to exist at the surface, while Mars, with roughly 1/10 Earth's mass, could only maintain a thin carbon dioxide atmosphere that provides insufficient pressure for stable liquid water. The escape velocity from a planet increases with its mass, making it harder for atmospheric gases to achieve the speeds needed to overcome gravity and drift away into space. Geological activity driven by the heat of planetary formation and radioactive decay in the planet's interior plays a less obvious but equally important role in maintaining long-term habitability. Plate tectonics on Earth recycle carbon dioxide from the atmosphere back into the mantle through subduction of oceanic crust, then release it again through volcanic eruptions, creating a thermostat that has kept our climate stable enough for liquid water throughout the planet's history, despite the sun's gradually increasing brightness. Volcanoes also replenish atmospheric gases that would otherwise be lost to space or locked into rocks, counteracting the slow erosion of the atmosphere that occurs even on planets with strong magnetic fields. Magnetic fields generated by convection currents in a planet's liquid metallic core shield the surface from stellar wind, the stream of charged particles constantly flowing outward from stars. Earth's magnetic field deflects most of the solar wind around the planet, preventing it from directly striking and gradually eroding our atmosphere. Mars likely had a magnetic field early in its history, when its interior remained hot enough to maintain convective motion. But as the planet cooled, its magnetic field shut down, leaving the atmosphere vulnerable to stripping by the solar wind over billions of years. The habitable zone concept represents just a starting point for evaluating whether a planet could support life, since atmospheres, magnetic fields, geological activity, and stellar characteristics all modify the simple calculation of orbital distance. A planet could orbit squarely in the middle of the habitable zone, yet remain completely sterile because it lacks an atmosphere to distribute heat and maintain surface pressure, or because its star bathes it in lethal radiation, or because it froze early in its history and never developed the geological recycling processes needed to maintain clement conditions. Conversely, worlds outside the traditional habitable zone might still harbour life under certain circumstances, particularly in subsurface oceans heated by tidal flexing or radioactive decay. Jupiter's moon, Europa, and Saturn's moon Enceladus both possess liquid water oceans beneath their icy shells, despite orbiting far beyond where surface liquid water could exist, kept warm by internal heat sources rather than sunlight. These ocean worlds expand the range of environments where life might arise, though such life would remain much harder to detect than organisms living on planetary surfaces. The chemistry of a planet's atmosphere provides another critical factor in habitability, with greenhouse gases like carbon dioxide and methane trapping enough heat to warm surfaces above the temperature they would reach from stellar radiation alone. Earth's average surface temperature would sit well below the freezing point of water if not for the greenhouse warming provided by our atmosphere, which elevates temperatures by about 33 degrees Celsius. Too much greenhouse warming leads to runaway effects like those on Venus, where surface temperatures exceed 460 degrees Celsius because a dense carbon dioxide atmosphere traps essentially all incoming solar radiation. Oxygen's presence in an atmosphere serves as a potential biosignature because oxygen is highly reactive and will quickly bind to other elements unless something continuously replenishes it. Earth's oxygen-rich atmosphere exists because photosynthetic organisms produce oxygen faster than geological and chemical processes consume it. And most scientists expect that finding oxygen in another planet's atmosphere would strongly suggest biological activity. However, some non-biological processes can also generate oxygen, so confirming life would require detecting multiple gases whose combined presence points to biological production. Water vapor in an exoplanet's atmosphere indicates that liquid water likely exists on the surface, because water vapor and liquid water remain in equilibrium at appropriate temperatures and pressures. Detecting water vapor requires analysing the spectrum of starlight that passes through the planet's atmosphere during transits, looking for the characteristic absorption patterns water molecules create at specific wavelengths. The James Webb Space Telescope has begun conducting these measurements on the most favourable targets, searching for water and other molecules that might indicate habitable conditions or even biosignatures. Proxima Centauri b, discovered in 2016, holds the distinction of being the closest known exoplanet to Earth at a distance of just 4.24 light-years. This planet orbits Proxima Centauri, a red dwarf star that serves as the third member of the Alpha Centauri system and our Sun's nearest stellar neighbour. The proximity makes Proxima Centauri b an obvious target for detailed study and has inspired proposals for interstellar probe missions that could reach the system within a human lifetime if technology continues advancing. Astronomers detected Proxima Centauri b using the radial velocity method after years of careful observations with spectrographs in Chile and around the world, part of a campaign called Pale Red Dot that sought to find planets around our nearest stellar neighbours. The planet has a minimum mass of at least 1.3 times Earth's mass, meaning it could be heavier if the orbital plane doesn't align perfectly edge-on to our line of sight. That mass places it firmly in the terrestrial planet category, rather than among the mini-Neptunes or gas giants that dominate the exoplanet catalogue. The planet completes one orbit every 11.2 days, circling Proxima Centauri at a distance of about 7.5 million kilometres, or roughly 5% of the distance between Earth and the Sun. This tight orbit would place the planet well inside Mercury's orbit if transferred to our solar system, but Proxima Centauri shines with only about 0.17% of the Sun's luminosity. The combination of the star's dimness and the planet's proximity positions Proxima Centauri b squarely within its star's habitable zone, where it receives about 65 to 70% of the stellar energy that Earth receives from the Sun. Scientists calculate that if Proxima Centauri b has an Earth-like atmosphere, its surface temperature could allow liquid water to persist in at least some regions. Computer models suggest the planet is very likely tidally locked with one hemisphere perpetually facing the star and the other locked in eternal darkness, a configuration that creates extreme temperature contrast between the two sides. The day side might be warm enough for liquid water, while the night side freezes solid, unless atmospheric circulation can transport enough heat to moderate temperatures across the entire planet. Proxima Centauri's intense stellar activity presents the most serious challenge to habitability on any planet orbiting in its habitable zone. The star regularly unleashes powerful flares that increase its brightness by factors of 10 or more, bombarding the planet with ultraviolet and X-ray radiation at levels hundreds of times stronger than Earth experiences from the Sun. These energetic outbursts can strip away atmospheric gases through photoevaporation, where high-energy photons break apart molecules and give atoms enough velocity to escape the planet's gravity. Theoretical models of atmospheric evolution suggest that Proxima Centauri b could have lost its entire atmosphere to stellar wind stripping and photoevaporation over the billions of years since its formation, if it started with only a thin atmosphere like Earth's. However, if the planet formed with a much more massive atmosphere initially, it might retain enough gases to support liquid water despite the continuous bombardment. Rocky planets can build thick atmospheres during formation by accumulating hydrogen and helium from the protoplanetary disk, then lose most of that light gas over time while retaining heavier molecules like water vapour, nitrogen and carbon dioxide. Whether Proxima Centauri b currently possesses an atmosphere remains unknown because the planet has never been observed transiting its host star, preventing direct measurement of atmospheric composition through transmission spectroscopy. The planet's orbit may not align properly for transits to occur from Earth's vantage point, a limitation that affects roughly 99% of exoplanets, since transit observations require specific geometric alignment. Future observations with extremely large ground-based telescopes or dedicated space missions might detect reflected light from the planet or measure its thermal emission, allowing indirect characterization of any atmosphere that exists. Proxima Centauri b's Earth Similarity Index, a measure combining factors like radius, density, escape velocity, and surface temperature, reaches approximately 0.87 on a scale where Earth scores 1.0. This relatively high score reflects the planet's similarity to Earth in mass and the amount of stellar energy it receives, though the score doesn't account for factors like stellar activity, tidal locking, or atmospheric retention that could render the world uninhabitable, despite its favourable position in the habitable zone. The planet's proximity to Earth makes it an attractive target for potential interstellar missions, though reaching even our nearest planetary neighbour presents staggering technological challenges. At the speeds achieved by the fastest spacecraft humans have launched, Voyager 1 travelling at about 61,000 km per hour relative to the Sun, the journey to Proxima Centauri would require more than 70,000 years. Breakthrough Starshot, an initiative announced in 2016, proposes sending tiny laser-propelled spacecraft to Alpha Centauri at 20% of light speed, which would allow flyby observations after about 20 years of travel time. Studying Proxima Centauri b helps astronomers understand the habitability prospects for planets around M-dwarf stars more generally, since these cool red stars outnumber all other stellar types and likely host billions of habitable zone planets throughout the galaxy. If stellar activity proves too destructive for atmospheres and life to persist on planets orbiting M-dwarfs, it would dramatically reduce the number of potentially habitable worlds in the universe. Conversely, finding that life can thrive despite flares and intense radiation would expand the galactic real estate where we should search for biosignatures. Proxima Centauri itself formed roughly 4.85 billion years ago, making it slightly older than our 4.6 billion-year-old Sun. The star will continue shining for trillions of years because M-dwarfs burn their hydrogen fuel so slowly, giving any life on Proxima Centauri b extraordinary amounts of time to develop if conditions permit. Earth's biosphere has existed for perhaps 3.5 billion years, occupying roughly 3/4 of our planet's history, and Proxima Centauri b could potentially support life for timescales that dwarf Earth's entire existence. The scientific community continues debating Proxima Centauri b's actual habitability, with some researchers arguing that the harsh radiation environment makes life implausible, while others suggest that protective mechanisms like strong magnetic fields or thick atmospheres might allow organisms to survive and flourish. Definitive answers will require direct observations of the planet's atmosphere if one exists, searching for gases that indicate active chemistry and potentially biological activity. The TRAPPIST-1 system, announced in February of 2017, represents one of the most remarkable discoveries in exoplanet science, with 7 Earth-sized planets orbiting a single ultra-cool dwarf star located 40 light-years from Earth in the constellation Aquarius. 3 of these planets, designated TRAPPIST-1 E, F, and G, orbit within the star's habitable zone where temperatures could allow liquid water to exist on their surfaces. Finding 7 terrestrial planets around one star with multiple candidates for habitability transformed TRAPPIST-1 into the most intensively studied exoplanetary system besides our own solar system. TRAPPIST-1, the host star, qualifies as an ultra-cool dwarf with a mass of only about 9% the Sun's mass and a radius similar to Jupiter despite being a star rather than a planet. Its surface temperature of roughly 2,500 Kelvin makes it much cooler and redder than the Sun, emitting most of its energy in the infrared rather than visible light. The star's low luminosity of only 0.5%. The Sun's brightness positions its habitable zone very close to the star, where all 7 planets orbit at distances smaller than Mercury's orbit around our Sun. Astronomers discovered the first hints of the TRAPPIST-1 system using the Transiting Planets and Planetesimal Small Telescope in Chile, observing what they initially thought were 3 transiting planets. Follow-up observations with NASA's Spitzer Space Telescope revealed the full family of 7 worlds, all of which transit the star from Earth's perspective because their orbital planes align almost perfectly with our line of sight. This fortunate alignment allows detailed study of the planet's sizes, masses, and atmospheric properties through techniques that require seeing planets pass in front of their star. The 7 planets complete orbits ranging from 1.5 days for the innermost world, TRAPPIST-1b, to roughly 20 days for the outermost planet, TRAPPIST-1h. The planets pack so tightly around their dim star that the entire system would fit inside Mercury's orbit if transplanted to our solar system, yet the reduced stellar output means the middle planets receive energy levels comparable to Earth, Venus, and Mars. Orbital resonances link many of the planets, with their orbital periods related by simple ratios that keep the system dynamically stable over billions of years. TRAPPIST-1e, the 4th planet from the star, has emerged as the most promising candidate for habitability among the 7 worlds. This planet has a radius of about 92% of Earth's radius, and a mass equivalent to 69% of Earth's mass, making it slightly less dense than our planet. The lower density could indicate either a different internal composition with more iron-poor rocks, or the presence of a significant water component, possibly in the form of a global ocean beneath an icy shell or as liquid water on the surface. the planet receives about 60% of the stellar flux that Earth receives from the Sun, positioning it in the middle of TRAPPIST-1's habitable zone, where temperatures should allow liquid water if the planet has an atmosphere. Its equilibrium temperature, calculated assuming no atmosphere, ranges from about 225 Kelvin to 246 Kelvin depending on the planet's reflectivity. An atmosphere with greenhouse gases would raise these temperatures, potentially creating conditions suitable for liquid water and life. James Webb Space Telescope observations of TRAPPIST-1a begun in 2023 have attempted to detect and characterize any atmosphere the planet might possess. Initial results in 2025 ruled out certain atmospheric scenarios, including thick hydrogen-rich atmospheres and atmospheres similar to Venus or Mars, but couldn't definitively confirm or deny the presence of a thinner Earth-like atmosphere. The search continues with additional observations planned to test whether TRAPPIST-1e maintains an atmosphere capable of supporting surface liquid water. TRAPPIST-1b and c, the two innermost planets, likely lack substantial atmospheres because they receive too much stellar energy to retain volatile gases over long timescales. Webb observations published in 2023 found these planets have minimal atmospheric content, appearing as bare, rocky worlds scorched by their proximity to the star. This atmospheric erosion results from the intense radiation and stellar wind that ultra-cool dwarfs like TRAPPIST-1 emit, particularly during their more active youth when flares and energetic outbursts occur more frequently. The potential for atmospheric retention on the outer planets, particularly TRAPPIST-1e, F and G, depends on factors including initial atmospheric mass, the strength of the stellar wind, and whether the planets possess magnetic fields to deflect charged particles. Computer models suggest that planets could begin with massive primordial atmospheres, rich in hydrogen, that gradually erode away, leaving behind heavier molecules like water vapor, nitrogen, and carbon dioxide. If the outer TRAPPIST-1 planets started with enough volatiles, they might retain atmospheres thick enough to support liquid water, despite billions of years of stellar bombardment. Research published in 2024 found that outer TRAPPIST-1 planets could have started with water inventories equivalent to hundreds of Earth oceans, losing most of that water to atmospheric escape while still retaining enough to maintain substantial oceans or ice deposits. The model suggests TRAPPIST-1e might be particularly water-rich if it formed farther from the star and migrated inward later in the system's evolution, accumulating volatiles from icy material in the outer disk before settling into its current orbit. All 7 TRAPPIST-1 planets are almost certainly tidally locked because of their proximity to the star and the age of the system, estimated at roughly 8 billion years old. Tidal locking could create day-night temperature extremes that challenge habitability, but recent climate models indicate that atmospheric circulation on planets with substantial atmospheres could transport enough heat from the day side to the night side to create habitable conditions in a ring around the terminator zone. Life might exist in this permanent twilight belt where temperatures allow liquid water without the extremes of full sunlight or total darkness. The compact arrangement of the TRAPPIST-1 system creates another intriguing possibility for life. If organisms arose on one planet, they might spread to others through a process called lithopanspermia. Asteroid or comet impacts can eject rocks from a planet's surface with enough velocity to escape that planet's gravity, and some fraction of those rocks could eventually cross paths with neighbouring planets and deliver any hardy organisms they carry. The close spacing of the TRAPPIST-1 planets would make such transfers more efficient than in our solar system, potentially allowing life to seed multiple worlds. TRAPPIST-1, F and G, the other 2 planets in the habitable zone, orbit farther from the star than TRAPPIST-1e and receive less stellar energy. TRAPPIST-1F completes an orbit every 9.2 days and receives about 40% of Earth's solar flux, while TRAPPIST-1G orbits every 12.4 days and receives about 25% of Earth's flux. Both planets could potentially support liquid water with appropriate atmospheric compositions, though they would likely be cooler on average than Earth, and might resemble ice-covered ocean worlds rather than planets with exposed liquid water oceans. The system's age of approximately 8 billion years gives life plenty of time to emerge and evolve if conditions permit, though the host star's variable activity during its youth might have sterilized any early biospheres before they could establish themselves. Ultra-cool dwarfs like TRAPPIST-1 remain relatively active throughout their lives compared to Sun-like stars, continuing to produce flares that could damage planetary atmospheres and any organisms on their surfaces. Whether life can adapt to such environments, or requires the calmer conditions provided by more massive, less active stars remains an open question. TRAPPIST-1 provides an ideal laboratory for studying planetary atmospheres because all 7 planets transit their star, allowing transmission spectroscopy measurements that reveal atmospheric composition. The star's small size relative to Sun-like stars means that planets block a larger fraction of starlight during transits, creating stronger signals that are easier to measure. This advantage has made TRAPPIST-1 one of the highest priority targets for atmospheric characterization with the James Webb Space Telescope, and will ensure the system receives intensive study for decades to come. Red dwarf stars, the small, cool, M-class stars that make up roughly 75% of all stars in the Milky Way, present a paradox for those searching for habitable worlds. These abundant stellar types offer billions of potential host stars for exoplanets and remain stable for trillions of years, giving life extraordinary amounts of time to evolve. However, the characteristics that make red dwarfs so numerous also create serious challenges for any planets orbiting in their habitable zones, challenges that might render most M-dwarf systems hostile to life as we understand it. The habitable zone around a red dwarf star sits extremely close to the star because of its low luminosity, typically at distances of just a few million to perhaps 50 million kilometers, depending on the star's specific mass and temperature. Planets must orbit tightly to receive enough stellar energy for liquid water, completing revolutions in days or weeks rather than months or years. This proximity to the host star subjects planets to intense tidal forces that gradually slow their rotation until one hemisphere permanently faces the star while the other remains in eternal darkness. Tidal locking creates extreme environmental challenges for habitability because the day side receives constant stellar bombardment that could evaporate oceans and drive away atmospheric gases, while the night side plunges into frigid cold where any water freezes solid and atmospheric gases might snow out onto the surface. The stark temperature contrast between eternally lit and permanently dark hemispheres could exceed hundreds of degrees Celsius, making both regions hostile to life unless substantial atmospheric circulation can moderate the extremes. Computer climate models developed over the past decade have investigated whether thick atmospheres can overcome tidal locking's challenges by transporting heat from hot day side to cold night side efficiently enough to maintain habitable temperatures in some regions. These simulations suggest that planets with Earth-like atmospheric masses might sustain a habitable band around the terminator zone separating day from night, where temperatures allow liquid water without the extremes of either hemisphere. Life in this perpetual twilight would exist under very different conditions from Earth's day-night cycle, but might adapt to the permanent red glow and stable temperatures. The stellar flares that red dwarfs produce represent perhaps the most serious threat to habitability around these small stars. Young M-dwarfs in particular undergo frequent powerful flares that temporarily increase their brightness by factors of 10 or more, unleashing torrents of ultraviolet and X-ray radiation. Proxima Centauri, the nearest red dwarf to Earth, produces flares with energies reaching 10,000 times the strongest solar flares, bombardments that would sterilize any exposed organisms and strip away atmospheric gases through photoevaporation. Atmospheric escape driven by stellar radiation occurs when high-energy photons strike molecules in a planet's upper atmosphere, breaking them apart into individual atoms and giving those atoms enough velocity to overcome the planet's gravity and drift into space. The process operates continuously on all planets, but accelerates dramatically during flare events when radiation intensity spikes. Over billions of years, this steady erosion can remove entire atmospheres from planets orbiting active M-dwarfs, leaving them as airless rocks incapable of supporting liquid water. Research published in 2017 modelled atmospheric escape rates for the TRAPPIST-1 planets, and found that the innermost worlds likely lost their atmospheres completely within tens to hundreds of millions of years after formation. The outer planets in the habitable zone might have retained atmospheres if they started with massive primordial envelopes rich in volatiles, accumulating enough water during formation to replenish losses from stellar bombardment. Whether such water-rich formation scenarios commonly occur around M-dwarfs remains uncertain. magnetic fields could provide some protection from stellar wind and flares by deflecting charged particles around the planet rather than allowing direct impact with the atmosphere. Earth's magnetic field, generated by convection currents in our planet's liquid iron outer core, shields us from the solar wind and reduces atmospheric escape rates substantially. However, generating strong magnetic fields requires planets to have hot liquid cores with vigorous convection, conditions that depend on planetary mass, composition, and thermal evolution. Smaller planets cool faster than larger ones because they have higher surface-to-volume ratios, allowing heat to escape more efficiently. Mars probably had a strong magnetic field early in its history, when its interior remained hot enough for liquid iron to convect. But as the planet cooled, its magnetic field shut down, leaving the atmosphere exposed to solar wind stripping. Whether exoplanets around M-dwarfs can maintain active magnetic fields long enough to matter for atmospheric protection depends on their individual masses and thermal histories. The question of how tidal locking affects magnetic field generation remains debated among planetary scientists. Tidal locking synchronizes a planet's rotation with its orbital period, slowing the rotation rate from potentially rapid initial spins to the sedate pace matching the orbital period. Earth's magnetic field depends partly on our planet's relatively rapid rotation, which helps drive convective motions in the outer core through the Coriolis effect. Slower rotation rates might weaken or eliminate magnetic fields even if the core remains liquid and hot enough for convection. Some researchers argue that planets can generate magnetic fields through other mechanisms even if they're tidally locked, such as thermal or compositional convection that doesn't require rapid rotation. Europa and Ganymede, moons of Jupiter that are tidally locked, appear to possess induced magnetic fields generated by interactions between Jupiter's magnetic field and conducting layers within the moons. Whether similar processes could protect exoplanet atmospheres remains unclear. The chemical composition of red dwarf stellar winds differs from the solar wind's composition because M-dwarfs have cooler surface temperatures that alter nuclear reactions in their atmospheres. These compositional differences might affect how stellar winds interact with planetary magnetic fields and atmospheres, potentially making M-dwarf winds more or less damaging than simple energy comparisons would suggest. Detailed modelling of these interactions requires understanding both the stellar wind properties and the planetary magnetic field configurations, both of which remain poorly constrained for most exoplanetary systems. Red dwarfs take much longer to settle onto the main sequence than more massive stars, spending hundreds of millions to billions of years in a pre-main sequence phase, where they remain highly active with intense flaring and strong stellar winds. Planets forming around M-dwarfs get bombarded by this energetic radiation from the moment they coalesce out of the protoplanetary disk, potentially losing their initial atmospheres before they fully form. Whether planets can later rebuild atmospheres through volcanic outgassing or remain permanently airless depends on their volatile inventories and geological activity levels. The spectral energy distribution of red dwarfs peaks in the infrared rather than visible wavelengths because of their cool surface temperatures, typically 2000 to 3500 Kelvin compared to the Sun's 5780 Kelvin. This altered spectrum affects photosynthesis for any hypothetical life on planets orbiting M-dwarfs, since Earth plants evolved to capture energy from sunlight's peak wavelengths in the visible range. Alien photosynthesis might adapt to harvest infrared wavelengths, using different photosynthetic pigments than the chlorophyll that gives Earth plants their green colour. Computer models of exoplanet atmospheres around M-dwarfs predict that oxygen could build up to high concentrations through non-biological processes, particularly photolysis of water molecules when ultraviolet radiation breaks water apart. This abiotic oxygen production could create false positive biosignatures if astronomers detect oxygen in an M-dwarf planet's atmosphere and assume it indicates life. Confirming biological activity would require finding oxygen combined with other gases, like methane, in proportions that only metabolism could maintain. Despite these challenges, the sheer abundance of M-dwarf stars means that potentially billions of planets orbit in habitable zones around them throughout our galaxy. If even a small fraction of these worlds manage to retain atmospheres and develop life, red dwarf planets could host the majority of living organisms in the Milky Way. The question of M-dwarf habitability will likely be answered observationally over the next few decades, as improved telescopes characterize the atmospheres of planets like those in the TRAPPIST-1 system. The debate over red dwarf habitability highlights how much we still don't understand about what makes planets suitable for life and which factors matter most. Is atmospheric retention more important than tidal locking effects? Do magnetic fields provide sufficient protection, or do they matter less than initial volatile inventories? Can life adapt to constant flare bombardment, or does such radiation inevitably sterilize surfaces? These questions will be answered through a combination of theoretical modelling, laboratory experiments, and direct observations of exoplanet atmospheres. Kepler 452b earned the nickname Earth's cousin when NASA announced its discovery on July 23, 2015, exactly 20 years after the first exoplanet around a main sequence star was confirmed. This planet orbits a G2-type star nearly identical to our Sun in temperature and spectral class, making Kepler 452b the first near-Earth-size world found in the habitable zone of a truly Sun-like star. The discovery marked a milestone in the search for Earth 2.0 by demonstrating that planets similar to ours orbit stars similar to the Sun, though substantial differences between Kepler 452b and Earth temper enthusiasm about its habitability. The planet lies approximately 1,400 light-years from Earth in the constellation Cygnus, discovered through analysis of data from NASA's Kepler Space Telescope. Kepler 452b orbits its host star once every 385 days, remarkably similar to Earth's 365-day year. Its orbital distance of about 1.05 astronomical units places it only 5% farther from its star than Earth orbits from the Sun, positioning Kepler 452b in the middle of its star's habitable zone, where liquid water could exist if the planet has appropriate atmospheric properties. Kepler 452b's radius measures approximately 1.63 times Earth's radius, making it about 60% larger in diameter than our planet. This size classifies Kepler 452b as a super-Earth, a category of planets more massive than Earth, but less massive than ice giants like Neptune and Uranus. The planet's exact mass remains uncertain because it hasn't been measured through radial velocity observations, but models suggest it could be 5 times Earth's mass if it has a rocky composition similar to our planet. The enhanced size and probable mass would give Kepler 452b surface gravity roughly twice as strong as Earth's, meaning objects and people would weigh twice what they weigh here. This higher gravity would compress the atmosphere to higher densities at the surface and might influence the planet's geological activity by increasing pressure on the mantle and core. Visitors from Earth would need time to adjust to the increased weight. Though humans routinely carry heavy backpacks and equipment that temporarily doubles the load on their bodies, suggesting adaptation would be possible. Kepler 452, the host star, burns about 20% brighter than the Sun with a similar surface temperature of 5757 Kelvin, compared to the Sun's 5778 Kelvin. The star's age of approximately 6 billion years makes it roughly 1.5 billion years older than our 4.6 billion-year-old Sun, placing it at a more evolved stage where increased fusion reactions have boosted its luminosity above solar values. As Sun-like stars age, they gradually become brighter and hotter. Consequences of changes in their core structure, as hydrogen fusion produces helium ash that alters the star's internal pressure and temperature distributions. The combination of Kepler 452b's orbital distance, similar to Earth's, and its star's enhanced brightness, means the planet currently receives about 10% more energy than Earth receives from the Sun. This extra heating could push Kepler 452b toward a runaway greenhouse effect similar to the one that transformed Venus from a potentially habitable world into the scorching hothouse we observe today. Venus receives nearly twice Earth's solar fleets because of its closer orbit, and that extra energy drove the evaporation of any oceans, filling the atmosphere with water vapor that created runaway greenhouse warming as the water molecules trapped solar radiation and temperatures soared. Scientists debate whether Kepler 452b has already undergone or will soon experience such a climatic catastrophe. If the planet formed with abundant water like Earth, the gradual brightening of its aging star combined with the already elevated energy input might have pushed it past the threshold where oceans evaporate and atmospheric water vapor creates unstoppable warming. Artist concepts of Kepler 452b sometimes depict it as a drying world, with evaporating seas and thick clouds, representing one possible evolutionary path for a planet receiving slightly too much stellar energy. Alternatively, Kepler 452b might have formed with less water than Earth, or it might possess atmospheric composition and cloud cover that reflect enough sunlight to maintain temperate surface conditions despite the enhanced energy input. White clouds covering a substantial fraction of the planet would increase its albedo, bouncing solar radiation back into space before it can warm the surface. Different initial conditions and evolutionary paths could produce wildly different outcomes for two planets receiving similar amounts of stellar energy. The planet's size places it in a category where scientists remain uncertain about likely composition. Current instruments can't determine definitively whether a super-Earth the size of Kepler 452b has a rocky surface like Earth or accumulated a thick atmosphere of hydrogen and helium like Neptune. Planets with radii between 1.5 and 2 times Earth's radius occupy this ambiguous zone where statistical studies suggest roughly even odds of being rocky versus gaseous. Below 1.5 Earth radii, planets appear almost exclusively rocky, while above 2 Earth radii they become increasingly likely to be mini-Neptunes with no solid surface. If Kepler 452b has a rocky composition, it would likely possess active geology with plate tectonics and volcanism, driven by its larger mass and higher internal pressures. The enhanced gravity would increase the weight bearing down on the mantle, potentially making plates easier to subduct and recycle back into the interior. Active plate tectonics could help regulate atmospheric carbon dioxide through the carbonate-silicate cycle that has kept Earth's climate stable over billions of years, giving Kepler 452b a better chance of maintaining habitable conditions despite its aging star. Kepler 452b has spent approximately 6 billion years in its star's habitable zone, according to calculations that account for the star's evolving brightness and the planet's orbital distance. This represents substantially longer than Earth's time in the habitable zone, giving life extraordinary amounts of time to emerge and evolve if other conditions permitted. However, spending 6 billion years in the habitable zone doesn't guarantee that life developed, since habitability requires much more than just the right temperature range. The planet's detection through the transit method allowed precise measurement of its size but provided no information about its mass, atmospheric composition, or surface properties. Kepler 452b's great distance of 1400 light-years makes it too faint for radial velocity follow-up with current instruments and far too distant for direct imaging or atmospheric characterization with existing telescopes. We may never know if Kepler 452b truly harbours life, or has already succumbed to a runaway greenhouse effect unless revolutionary new detection methods emerge. The discovery of Kepler 452b demonstrated that the combination of Earth-like orbital distances and Sun-like host stars occurs in nature, validating theoretical predictions that planets similar to Earth should orbit stars similar to the Sun. This finding suggests that true Earth analogues likely exist by the billions throughout the galaxy, though finding them requires multi-year monitoring campaigns to detect the small number of transits visible from Earth for planets with year-long orbits. Kepler 186f, discovered in April 2014, became the first Earth-sized planet found orbiting in the habitable zone of another star, a milestone achievement that demonstrated small rocky planets exist at distances where liquid water could be maintained. This planet orbits a red dwarf star approximately 500 light-years away and completes one orbit every 130 days, receiving about 32% of the stellar flux that Earth receives from the Sun. The reduced energy input positions Kepler 186f near the outer edge of its star's habitable zone, where it would need a substantial atmosphere with greenhouse warming to prevent surface water from freezing. The planet's radius of just 10% larger than Earth's makes it the most Earth-like in size of all known exoplanets in habitable zones, though its orbit around a red dwarf rather than a Sun-like star creates a very different environment from our homeworld. Kepler 186, the host star, shines with only 4% of the Sun's luminosity, bathing its planets in dim reddish light that would make photosynthesis challenging for organisms evolved in sunlight, but might still support alternative biochemistries adapted to infrared wavelengths. Kepler 442b orbits an orange K-type star roughly 1200 light-years distant and completes each orbit in 112 days, while receiving about 69% of Earth's solar flux. This planet, discovered in 2015, has a radius about 1.3 times Earth's radius and sits comfortably within its star's habitable zone. Remarkably, studies have calculated that Kepler 442b might have a higher likelihood of being habitable than Earth itself based on the amount of light it receives for photosynthesis, earning it an Earth Similarity Index score of 0.84 compared to Earth's 0.83. The unusual result occurs because habitability metrics don't measure actual habitability, but rather how closely planetary parameters match Earth's values. Kepler 442b receives slightly less light than Earth, but not so little that photosynthesis becomes impossible, and its K-type host star burns cooler and longer lived than the Sun, potentially providing more stable conditions over billions of years. K-stars, sometimes called Goldilocks stars, combine some advantages of both Sun-like G-stars and smaller M-dwarfs, offering long lifetimes without the intense flaring activity that plagues the smallest red dwarfs. TOI 700d, identified by the TESS mission and confirmed in January 2020, became TESS's first Earth-sized habitable zone planet discovery. This world orbits an M-dwarf star about 100 light-years away, completing each orbit in 37 days while receiving approximately 86% of Earth's solar flux. Computer climate models suggest TOI 700d could maintain liquid water on its surface, with various possible atmospheric compositions, from thin Earth-like atmospheres to thicker carbon dioxide-rich envelopes that would create more intense greenhouse warming. Gliese 667 cc, announced in 2011, orbits a red dwarf that itself belongs to a triple star system located 22 light-years from Earth. The planet completes orbits every 28 days and receives about 90% of the stellar energy that Earth receives from the Sun, placing it near the inner edge of the habitable zone where temperatures might allow liquid water with appropriate atmospheric composition. However, the planet orbits close enough to its host star that it likely experiences powerful flares that could strip atmospheric gases over time. Teegarden's Star B, discovered through radial velocity measurements in 2019, orbits just 12.5 light-years from Earth around a small red dwarf. This planet initially earned an Earth Similarity Index score of 0.97, nearly perfect, though later refinements dropped that score to approximately 0.9 as better measurements improved understanding of the system. The planet completes orbits every 5 days at a distance of only 0.0252 astronomical units from its dim host star, and researchers estimate about a 60% chance that liquid water exists on the surface. Ross 128b circles a quiet M-dwarf star located 11 light-years from Earth, making it one of the closest known exoplanets and the closest temperate world orbiting an inactive red dwarf. The planet has at least 1.4 times Earth's mass and completes orbits every 10 days, receiving about 38% more stellar energy than Earth receives from the Sun. Ross 128's low activity level gives its planet better prospects for retaining an atmosphere compared to more flare-prone red dwarfs, though the planet likely remains tidally locked with permanent day and night sides. Kepler 62f, orbiting approximately 1,200 light-years distant, resides in the outer region of its star's habitable zone and completes orbits every 267 days. The planet has a radius 40% larger than Earth's and likely possesses substantial amounts of water if it formed in the colder outer regions of its system before migrating inward. Computer models suggest Kepler 62f could maintain an ocean-covered surface with thick carbon dioxide atmospheres that provide greenhouse warming, or it might be an icy world with frozen oceans depending on atmospheric composition. Kepler 1649c, found through reanalysis of Kepler data in 2020, orbits 300 light-years away and has nearly identical size to Earth, with a radius just 6% larger. The planet receives about 75% of the stellar flux that Earth receives and completes orbits every 19.5 days around a red dwarf host star. The reanalysis that revealed this planet demonstrates that exoplanet catalogues likely contain additional undiscovered worlds that automated algorithms missed during initial processing. LHS 1140b, a super-Earth orbiting 41 light-years away, receives about 43% of Earth's solar flux while completing orbits every 25 days. This planet has about 5 times Earth's mass and significantly higher density than most super-Earths, suggesting either an iron-rich interior or a rocky composition with minimal atmosphere. Recent observations with James Webb Space Telescope hint at the possible presence of nitrogen in the planet's atmosphere, which if confirmed would mark the first detection of this essential atmospheric component on an exoplanet. Each of these worlds teaches researchers something different about the range of potentially habitable environments that exist throughout the galaxy. Some orbit sun-like stars while others circle dim red dwarfs. Some maintain longer orbits similar to Earth's year, while others race around their stars in days. And their varied masses and sizes span the range from slightly smaller than Earth to several times more massive. This diversity reflects the incredible variety of planetary systems that form around different types of stars. The common thread connecting these candidates is their position in their star's habitable zones, where liquid water could exist given appropriate atmospheric conditions. However, being in the habitable zone provides no guarantee of actual habitability, and scientists expect that many or even most worlds orbiting at the right distance from their stars will prove uninhabitable when examined in detail. Venus sits in the Sun's habitable zone but clearly doesn't support life, demonstrating that orbital distance alone cannot determine a planet's fate. Future observations with more powerful telescopes will begin separating the truly habitable worlds from those that merely occupy the right orbital real estate, searching for atmospheric biosignatures like oxygen combined with methane that would indicate biological activity. Until then, we can only say that these planets orbit where life might exist, not that life has actually emerged there. Understanding how potentially habitable planets form requires tracing their origins back to the protoplanetary disks of gas and dust that surround young stars, massive rotating clouds where planets coalesce from countless collisions between smaller bodies. The process begins when a molecular cloud collapses under its own gravity, fragmenting into individual protostars surrounded by disks of leftover material. These disks contain all the ingredients for planet formation, from rocky minerals and metals to icy compounds and gases, distributed in zones determined by temperature gradients that depend on distance from the central star. The frost line, located at the orbital distance where temperatures drop low enough for water ice to condense, divides protoplanetary disks into distinct regions with different compositions. Inside the frost line, only materials with high melting points like silicates and metals can exist in solid form, limiting the amount of mass available for planet building to perhaps 1% of the disk's total mass. Outside the frost line, water ice and other volatile compounds freeze solid, increasing the available mass by factors of 3 to 5 and allowing much larger planetary cores to form. Rocky planets like Earth form through a hierarchical process called accretion, where dust grains stick together through electrostatic forces and van der Waals interactions to form pebbles. Pebbles collide and merge into boulders, and boulders accumulate into planetesimals measuring kilometers across. These planetesimals represent the first objects massive enough for gravity to dominate their growth, pulling in additional material from their orbital neighborhoods and gradually clearing zones around their orbits. Hundreds to thousands of planetesimals form in the inner disk, destined to collide and merge over millions of years into terrestrial planets. The timeline for terrestrial planet formation extends from hundreds of thousands of years for initial dust coagulation to tens of millions of years for planets to reach their final masses. Computer simulations following the dynamical evolution of hundreds of planetary embryos show that planetary systems undergo chaotic periods with close encounters, collisions and ejections that determine the final number and orbital spacing of surviving planets. These simulations reproduce solar system-like architectures with rocky inner planets and gas giants farther out, but they also generate alternative configurations depending on initial conditions and random gravitational interactions. Gas giant formation requires building massive rocky cores before the protoplanetary disk dissipates, typically within a few million years of the star's birth. The core accretion model proposes that gas giants form when rocky icy cores grow to roughly 10 Earth masses, at which point their gravity becomes strong enough to capture massive envelopes of hydrogen and helium from the surrounding disk. This runaway gas accretion continues until the disk depletes or dissipates, determining the final mass of the giant planet. Jupiter and Saturn formed this way, building cores in the cold outer solar system where ices increased the available solid material. Alternative formation scenarios like disk instability propose that gas giants can form directly from gravitational collapse of dense regions in massive protoplanetary disks, bypassing the slow core accretion phase. This mechanism might explain the most massive planets discovered around some stars, particularly young giants found at large orbital distances where core accretion would take longer than the disk's lifetime. Whether disk instability operates in nature and how commonly it contributes to planetary populations remain active research questions. Planetary migration, the process where planets move inward or outward from their formation locations through gravitational interactions with the disk or other planets, profoundly influences final planetary system architectures. Type 1 migration affects smaller planets that remain embedded in the disk, with gravitational interactions between the planet and surrounding gas causing the planet's orbit to decay inward over timescales of thousands to millions of years. This migration can be rapid enough to send newly formed planets spiraling into their stars unless some mechanism halts the inward drift. Type 2 migration operates on massive planets that open gaps in the protoplanetary disk by clearing their orbital neighborhoods, with the planet locked into the gap and migrating inward as viscous processes cause the disk to accrete onto the star. This slower migration explains how hot Jupiters reach their current close-in orbits, despite forming beyond the frost line where ice exists. The planet spirals inward through the disk over millions of years, eventually parking in a tight orbit when the disk dissipates and migration ceases. Planet-planet scattering provides an alternative migration mechanism that doesn't require the protoplanetary disk to persist, operating instead through gravitational interactions between giant planets in unstable orbital configurations. When two massive planets' orbits cross or come too close, they engage in gravitational encounters that typically eject one planet from the system, while sending the other into either a tight orbit or a very elongated eccentric orbit. This dynamical process can generate hot Jupiters from initially widely separated gas giants without requiring disk migration. The Grand Tack hypothesis proposes that Jupiter migrated inward to perhaps 1.5 astronomical units from the Sun before reversing direction and moving back outward, explaining several puzzling features of our solar system's architecture. According to this model, Jupiter's inward migration truncated the inner disk and prevented Mars from growing to Earth's size, while the subsequent outward migration scattered planetesimals that later formed the asteroid belt. Saturn's formation and outward migration triggered Jupiter's reversal through a gravitational resonance that altered both planets' orbital evolution. Water delivery to Earth-like planets represents a crucial question for habitability, because planets forming inside the frost line start with little water, having coalesced from dry rocky materials. The water now present in Earth's oceans, atmosphere and crust must have arrived later through bombardment by water-rich asteroids and comets scattered inward from the outer solar system. Determining how efficiently this process operates, and whether Earth-like water abundances commonly occur on terrestrial planets, informs estimates of how many potentially habitable worlds exist. The timing of giant planet formation influences water delivery rates, because gas giants act as gravitational shepherds that either scatter icy planetesimals inward toward terrestrial planets or eject them from the system entirely. Jupiter's early formation may have reduced water delivery to Earth, compared to systems where giant planets form later or not at all, suggesting Earth might be relatively dry compared to terrestrial planets in other systems. Conversely, systems with no giant planets might receive less water because nothing scatters icy material from the outer disk toward rocky inner planets. Atmospheric composition on terrestrial planets depends partly on what gases the protoplanetary disk contained, and partly on subsequent processes like volcanic outgassing and atmospheric escape. Primary atmospheres of hydrogen and helium captured directly from the disk can be lost through photoevaporation when stellar ultraviolet radiation heats the upper atmosphere and gives gas molecules enough energy to escape. Secondary atmospheres form later from volcanic eruptions that release gases trapped in the planet's interior during formation, gradually building envelopes of water vapor, carbon dioxide, nitrogen and other compounds. The Late Heavy Bombardment, a period roughly 4 billion years ago when Earth and other inner solar system bodies experienced intense impacts from asteroids and comets, may have delivered substantial volatiles including water and organic compounds. Whether similar bombardment events commonly occur in other planetary systems depends on their specific dynamical histories and the efficiency of planetary migration in scattering small bodies. Systems with different giant planet architectures might experience earlier, later, or more intense bombardment phases that could enhance or reduce habitability. Planetary composition varies with formation location and migration history, because planets incorporate whatever materials exist in their formation zones. Terrestrial planets forming close to their stars accrete primarily refractory elements with high melting points, producing metal-rich dense worlds like Mercury. Planets forming farther out incorporate more volatiles, including water ice, producing less dense compositions with potential ocean layers. Planets that migrate through multiple disk zones might have mixed compositions reflecting their complex histories. The chemical makeup of the host star influences what materials are available for planet formation, with higher metallicity stars possessing more heavy elements from previous stellar generations, and therefore more raw material for building rocky planets and cores. Observations confirm that gas giant planets are more common around high metallicity stars, supporting core accretion models that require building large cores before gas capture can begin. Whether this metallicity correlation extends to terrestrial planets and affects their habitability remains less certain. Circumstellar habitable zones shift outward as stars evolve and brighten over billions of years, meaning planets that formed outside the habitable zone might later warm enough for liquid water, while originally habitable worlds eventually become too hot. This migration of the habitable zone complicates long-term habitability because a planet must remain in the zone long enough for life to emerge and evolve, typically estimated at hundreds of millions to billions of years. Stars like the Sun gradually brighten by roughly 10% per billion years, pushing their habitable zones steadily outward. The architecture of planetary systems affects habitability through dynamical interactions that can destabilize orbits or trigger massive impacts. Systems with giant planets on eccentric orbits might gravitationally perturb terrestrial planets, preventing stable climates or ejecting them from the system entirely. Conversely, giant planets on circular orbits at appropriate distances can protect inner terrestrial planets by deflecting asteroids and comets that might otherwise impact and damage developing biospheres. Jupiter likely plays this protective role for Earth, though the magnitude of the effect remains debated. Planet formation around binary and multiple star systems introduces additional complexities because planets must navigate the gravitational fields of two or more stars. Circumbinary planets orbit both stars at distances large enough to maintain stable orbits despite the stars' mutual motion, while circumstellar planets orbit just one member of a binary pair at distances small enough that the companion star's gravity doesn't destabilize the orbit. Both configurations occur in nature, with several confirmed circumbinary planets, including some in potential habitable zones. The diversity of planetary system architectures observed around other stars demonstrates that planet formation proceeds differently under varying initial conditions, from disk mass and composition to stellar multiplicity and local environment. Some systems contain hot Jupiters with no other detected planets, others host tightly packed systems of super-Earths, and still others resemble our solar system with rocky planets inside and gas giants outside. This architectural diversity suggests that potentially habitable worlds form through multiple pathways and might exist in a wide range of system configurations. Distance represents the most obvious obstacle to studying potentially habitable exoplanets in detail, since even the closest candidates lie light years away and require millions of years to reach at current spacecraft speeds. Proxima Centauri b, our nearest exoplanetary neighbour at 4.2 light-years, would take more than 70,000 years to reach using conventional rockets travelling at the speeds achieved by Voyager 1. The vast gulfs separating us from these worlds mean we cannot send robotic probes to explore them directly, and must instead rely on remote observations that reveal only basic properties like size, mass, and orbital parameters. The transit method that discovered most known exoplanets introduces strong observational biases because it only detects planets whose orbital planes happen to align with our line of sight. Statistically, only about 0.5% of planetary systems orient edge-on from Earth's perspective, meaning we miss more than 99% of all planets because their orbits don't produce transits. This geometric selection effect becomes especially severe for planets in wide orbits around Sun-like stars, since Earth-like worlds have only small chances of transiting even when the orbital plane aligns favourably. Radial velocity measurements face similar biases because planets produce stronger signals when their orbits appear edge-on, and the technique favours detecting massive planets in close orbits that induce larger stellar wobbles. Earth-sized planets in year-long orbits around Sun-like stars create velocity wobbles of only about 10 centimeters per second, approaching the fundamental limits of precision that current spectrographs can achieve. Detecting these subtle signals requires years of patient observations and sophisticated analysis to separate genuine planetary signals from false positives caused by stellar activity. Atmospheric characterization through transmission spectroscopy works only for the small fraction of exoplanets that transit their stars, and the strength of the signal depends on the planet's size, the star's size, and the thickness of the atmosphere. An Earth-sized planet transiting a Sun-like star creates atmospheric signals so weak that even the James Webb Space Telescope struggles to detect them clearly. Small, cool M-dwarf stars provide the best targets for atmospheric studies because planets block larger fractions of the smaller star's light, creating stronger signals that remain marginally detectable with current instruments. The challenge of distinguishing rocky planets from mini-Neptunes has emerged as a critical issue because planets with radii between 1.5 and 2.5 times Earth's radius could be either large rocky worlds or small gaseous planets without solid surfaces. Current telescopes can measure planetary radii through transit observations and estimate masses through radial velocity or transit timing variations, allowing density calculations that provide clues about composition. However, these measurements carry substantial uncertainties, and planets with similar densities could have very different structures depending on their formation history and atmospheric evolution. Tidal locking affects most exoplanets in habitable zones around M-dwarf stars because these planets orbit very close to their dim, host stars, where tidal forces quickly synchronize rotation with orbital motion. A tidally locked planet always presents the same face to its star, potentially creating extreme temperature gradients that concentrate all surface heat on the day side, while the night side freezes into a permanent ice sheet. Whether thick atmospheres can overcome this challenge by circulating heat from day to night remains uncertain, with different climate models producing contradictory results depending on their assumptions. Stellar radiation from active red dwarf stars poses another severe challenge for habitability around the galaxy's most common stellar type. Many M-dwarfs produce powerful flares that can temporarily increase the star's brightness by factors of 10 or more, bombarding their planets with intense ultraviolet and X-ray radiation. These energetic outbursts can strip away planetary atmospheres through photoevaporation, sterilize any life on exposed surfaces, and damage the complex organic molecules that biochemistry requires. The concept of planetary habitability itself rests on assumptions drawn from Earth's example, particularly the requirement for liquid water and carbon-based chemistry. Alien life might use completely different solvents like ammonia or liquid methane and build its biochemistry around elements other than carbon, potentially thriving under conditions we would consider uninhabitable. However, scientists focus the search for life on water-based chemistry around stars like the Sun because that's the only combination we know produces living organisms, and detecting truly alien biochemistries would require knowing what signatures to search for. The age of the host star influences habitability in complex ways because stars evolve over billions of years, gradually becoming brighter and shifting the boundaries of their habitable zones outward. A planet that formed in the habitable zone might become too hot billions of years later as its star ages and brightens, or a planet that started outside the habitable zone might eventually warm enough for liquid water when stellar evolution increases the star's energy output. Determining whether a planet is actually habitable requires understanding both its current conditions and its past climate history. False positives plague exoplanet detection, with eclipsing, binary star systems, star spots, and other astrophysical phenomena sometimes mimicking the signals that planets create. Validating planet candidates requires extensive follow-up observations and statistical analysis to rule out these alternative explanations, work that can take years for individual systems. Many exoplanets announced in recent years remain candidates, rather than confirmed planets, because the necessary follow-up observations haven't been completed yet. The habitable zone concept oversimplifies the requirements for habitability by reducing them to a single parameter, orbital distance, when dozens of factors influence whether a planet can support life. Atmospheric composition, magnetic field strength, geological activity, orbital eccentricity, stellar variability, and planetary mass all contribute to the complex question of habitability. Two planets at identical distances from identical stars might have completely different surface conditions depending on their individual properties and evolutionary histories. Runaway greenhouse effects represent an insidious threat to habitability because they can transform potentially habitable worlds into scorching hellscapes through feedback processes that amplify initial warming. Venus likely experienced a runaway greenhouse as increasing solar luminosity evaporated its oceans, filling the atmosphere with water vapor that trapped heat and drove temperatures higher in a self-reinforcing cycle. Once initiated, runaway greenhouses appear essentially irreversible, rendering planets permanently uninhabitable. The atmospheric escape problem becomes especially acute for planets orbiting dwarf stars, because these small, cool stars take billions of years to settle onto the main sequence, spending their youth in highly active states with intense radiation output. Planets forming around M dwarfs get bombarded by this radiation before their stars calm down, potentially losing their initial atmospheres completely. Whether such planets can later rebuild atmospheres through volcanic outgassing or remain sterile airless rocks throughout their lifetimes remains an open question. Scientists studying potentially habitable exoplanets must acknowledge the vast uncertainties inherent in characterizing worlds they can never visit directly, where measurements are difficult and incomplete, and where theoretical models rely on extrapolating from Earth's single example of a life-bearing planet. Each new discovery raises as many questions as it answers, gradually refining our understanding of what makes worlds habitable, while revealing additional complexities we hadn't previously considered. The James Webb Space Telescope, launched on Christmas Day 2021, has begun the era of detailed atmospheric characterization for exoplanets, particularly targeting small potentially habitable worlds orbiting nearby M-dwarf stars. Webb's infrared sensitivity allows it to detect molecules like water vapor, carbon dioxide, methane, and oxygen in exoplanet atmospheres by measuring the spectrum of starlight that filters through those atmospheres during planetary transits. The telescope has already studied TRAPPIST-1 planets and other priority targets, searching for biosignatures or evidence of unusual atmospheric chemistry that might indicate life. Webb's capabilities remain limited to the most favourable targets where small planets transit small, nearby stars, creating signals just strong enough for the telescope's instruments to detect above the noise. An Earth-sized planet transiting a Sun-like star would create signals too weak for Webb to characterise reliably, meaning true Earth analogues around solar twins will likely remain beyond its reach. Despite these limitations, Webb represents a massive step forward from previous instruments and has already delivered observations that constrain atmospheric properties on potentially habitable worlds. The telescope operates at a gravitational balance point called the second Lagrange point, positioned 1.5 million kilometers from Earth on the side opposite the Sun. This location allows Webb's sunshield to protect its sensitive infrared instruments from solar radiation while maintaining communication with Earth and avoiding the planet's shadow that would complicate observations. The observatory's massive 6.5-meter primary mirror and state-of-the-art detectors provide unprecedented sensitivity for studying exoplanet atmospheres, though each observation requires careful planning and substantial telescope time. Ground-based extremely large telescopes currently under construction will complement Webb's capabilities by providing even larger mirrors and different observing strategies. The extremely large telescope, being built by the European Southern Observatory in Chile's Atacama Desert, will feature a primary mirror 39 meters in diameter, composed of 978 individual segments. This gigantic light-gathering power, combined with adaptive optics systems that correct for atmospheric distortion, will enable direct imaging of some exoplanets and detailed spectroscopic studies of their atmospheres. The giant Magellan telescope and the 30-meter telescope, also under development, will join the extremely large telescope in pushing ground-based astronomy to new frontiers. These instruments will excel at high-resolution spectroscopy and direct imaging, potentially capturing photographs of Earth-like planets around nearby stars and analysing the chemical composition of their atmospheres. Adaptive optics systems using laser guide stars will partially compensate for the blurring effects of Earth's atmosphere, achieving image quality that approaches space-based observations for some wavelengths. The Plato mission, planned for launch by the European Space Agency in 2026, will search for Earth-like planets around Sun-like stars by monitoring hundreds of thousands of bright stars for transit signals. Unlike Kepler, which stared at one distant star field, Plato will observe bright nearby stars that enable detailed follow-up characterization of discovered planets. The mission's goal includes finding Earth-sized planets in year-long orbits around Sun-like stars, detections that require multi-year monitoring campaigns, and high-precision photometry to reveal the subtle dimming patterns created by planets similar to our own. NASA's Habitable Worlds Observatory, currently in early planning stages, aims to directly image and characterize potentially habitable exoplanets around nearby Sun-like stars. This space telescope would use starlight suppression techniques like coronagraphs to block the overwhelming glare from stars while preserving the faint signals from orbiting planets. The observatory would search for biosignatures in planetary atmospheres, particularly looking for oxygen combined with methane or other chemical combinations that suggest biological activity rather than geological processes. Detecting biosignatures remains extraordinarily challenging because several non-biological processes can produce the same gases that life generates on Earth. Oxygen, often considered a key biosignature, can be created by photolysis of water molecules in planetary atmospheres when ultraviolet radiation breaks water apart into hydrogen and oxygen. Methane, another potential biosignature, vents from volcanoes and forms through geological reactions that don't require life. Confirming biological activity likely requires detecting multiple gases together in combinations that only life produces, such as oxygen and methane coexisting, despite their tendency to react and neutralize each other. The search for technosignatures, evidence of alien technology rather than mere biology, represents another frontier in exoplanet studies. The SETI Institute and other organizations conduct searches for radio transmissions, laser pulses, or other artificial signals that advanced civilizations might emit. Breakthrough. LISTEN, a 10-year program begun in 2015, surveys millions of stars across multiple wavelengths, searching for narrow-band radio signals or optical pulses that natural astronomical sources cannot explain. So far, these searches have found no convincing evidence of alien technology, but they have only examined a tiny fraction of possible signal types and target systems. Transit timing variations, subtle changes in when transits occur caused by gravitational interactions between planets, allow detection of non-transiting planets in systems where at least one planet transits the star. This technique has revealed additional planets in several known systems and shows particular promise for finding Earth-mass planets whose direct transits create signals too weak to detect reliably. As observational precision improves, transit timing analysis will uncover fainter signals from smaller planets that current methods miss. Gravitational microlensing, where a foreground star's gravity focuses light from a background star and any orbiting planets create characteristic brightness patterns, excels at finding planets at large orbital distances where other methods struggle. This technique has discovered several potentially habitable worlds and remains the only method capable of detecting true Earth analogues at Earth-like distances from Sun-like stars without requiring decades of monitoring. However, microlensing events are unique and non-repeating, preventing follow-up observations of the discovered planets in most cases. Atmospheric observations of exoplanets will gradually improve as larger telescopes and more sensitive instruments come online, allowing characterization of smaller planets around brighter stars. Within the next 2 decades, astronomers should measure atmospheric composition for dozens of potentially habitable worlds, searching for biosignatures and unusual chemistry that might indicate life. These observations will test whether life commonly emerges on planets with the right conditions, or whether Earth represents something rare and precious in the cosmic landscape. The philosophical implications of finding life on another planet would reshape humanity's understanding of our place in the universe, answering the ancient question of whether we're alone while raising new questions about how common intelligent life becomes and whether civilizations inevitably destroy themselves before achieving interstellar communication. Alternatively, finding that potentially habitable worlds commonly lack biosignatures would suggest that life's emergence requires extraordinary luck or special circumstances that Earth happen to satisfy, but most planets do not. Interstellar travel to actually visit these worlds and confirm their habitability through direct exploration remains far beyond current technological capabilities, requiring either breakthrough propulsion systems or generation ships that would take thousands of years to reach even nearby stars. Breakthrough Starshot's proposal to send gram-scale probes at 20% of light speed using laser propulsion represents one possible path to interstellar reconnaissance, though the engineering challenges of building and operating such a system remain formidable. The coming decades will reveal whether planets like Earth commonly orbit stars like the Sun, or whether our world represents a rare combination of circumstances unlikely to be duplicated elsewhere. This knowledge will determine whether humanity's long-term future includes spreading to other worlds within our galaxy, or whether we remain confined to this single planet for all time. Detecting life on planets orbiting distant stars requires identifying biosignatures, chemical or physical indicators that biological processes created features we can observe from Earth. The most promising biosignatures involve atmospheric gases that organisms produce faster than geological or photochemical processes can consume them, creating concentrations that wouldn't persist without continuous biological replenishment. Oxygen in Earth's atmosphere exists almost entirely because photosynthetic organisms produce it relentlessly, since oxygen readily reacts with rocks, metals, and organic compounds, and would disappear within millions of years if life vanished. The combination of oxygen with methane in an atmosphere serves as an especially strong potential biosignature, because these two gases react with each other and neutralize over relatively short timescales. Finding them coexisting suggests something, likely biology, continuously produces both gases faster than they can react and disappear. On Earth, photosynthetic organisms generate oxygen, while methanogenic bacteria and larger organisms, through their metabolisms, produce methane, creating the disequilibrium chemistry that characterizes our atmosphere. Atmospheric transmission spectroscopy during planetary transits provides the primary method for analyzing exoplanet atmospheric composition from light years away. When a planet passes between its star and Earth, a tiny fraction of the starlight filters through the planet's atmosphere before reaching our telescopes. Different molecules in the atmosphere absorb specific wavelengths of light, creating characteristic patterns in the spectrum that reveal which gases are present and in what concentrations. Water vapor creates broad absorption features across multiple wavelengths because water molecules vibrate and rotate in numerous ways, each absorbing light at characteristic energies. Carbon dioxide produces sharp absorption lines at specific infrared wavelengths, where its molecular bonds vibrate when struck by photons of those exact energies. Oxygen creates features in the visible and near-infrared, while methane absorbs strongly in several infrared bands. By carefully analysing which wavelengths get absorbed during transits, astronomers can determine the atmospheric composition. The James Webb Space Telescope revolutionised atmospheric characterization by providing infrared sensitivity and collecting power far beyond previous instruments, though even Webb faces substantial challenges characterizing Earth-sized planets around Sun-like stars. The amount of light absorbed by a planet's atmosphere during a transit depends on the atmosphere's thickness, the planet's size relative to its star, and the molecular abundances of different gases. An Earth-like planet transiting a Sun-like star creates atmospheric signals spanning only tens of parts per million, requiring extraordinary measurement precision to detect. M-dwarf stars provide the best targets for atmospheric characterization because their small size relative to Sun-like stars means planets block larger fractions of starlight during transits, creating stronger signals. A planet identical to Earth transiting an M-dwarf creates atmospheric signals perhaps 10 times stronger than the same planet transiting a Sun-like star, bringing detection within reach of current instruments. This observational advantage explains why TRAPPIST-1 and similar systems around small red dwarfs receive such intensive study despite questions about their actual habitability. Biosignature gases must be detectable in concentrations high enough to stand out against the noise inherent in spectroscopic measurements, which depends both on the gas abundance and the strength of its absorption features. Oxygen on Earth exists at 21% of atmospheric molecules, creating strong absorption features easily detectable if Earth transited the Sun from an alien perspective. Other potential biosignatures like phosphine, dimethyl sulfide, or certain halocarbons might indicate life but exist at much lower concentrations, requiring larger telescopes and longer observation times to detect. False positives represent a serious concern when searching for biosignatures, because several non-biological processes can produce gases that life also creates. Photolysis of water vapour by ultraviolet light can generate oxygen without biology, particularly in the upper atmospheres of planets orbiting active M-dwarf stars. Methane vents from geological sources like volcanoes and mid-ocean ridges, creating atmospheric concentrations unrelated to biological activity. Identifying true biosignatures requires finding combinations of gases or isotope ratios that only biology produces. The search for biosignatures expands beyond simple atmospheric composition to include more subtle indicators like seasonal variations in gas concentrations, unusual isotope ratios, or the presence of industrial pollution. On Earth, atmospheric carbon dioxide and oxygen concentrations vary seasonally because plant growth and decay follow annual cycles. Detecting similar variations on an exoplanet might suggest photosynthetic organisms responding to changing illumination as the planet orbits its star or rotates through day-night cycles. Isotope ratios, the relative abundances of different atomic variants of the same element, can reveal biological processing because organisms preferentially use lighter isotopes in their metabolisms. Life on Earth enriches organic matter in carbon-12, relative to carbon-13 compared to non-biological carbon sources, a signature that persists in atmospheric gases and could potentially be detected on exoplanets with sufficiently precise spectroscopic measurements. However, measuring isotope ratios remotely requires resolving extremely fine spectral features that current instruments struggle to distinguish. Industrial pollution gases like chlorofluorocarbons would provide unambiguous evidence of technological civilization if detected in an exoplanet atmosphere, since these compounds do not occur naturally, and Earth's atmosphere contained none until humans began manufacturing them. The search for such technosignatures parallels traditional CT efforts to detect artificial radio transmissions, expanding the hunt for extraterrestrial intelligence to include chemical markers of industrial activity rather than just deliberate communications attempts. Surface biosignatures offer another avenue for detecting life, particularly looking for the reflection spectra that vegetation or other photosynthetic organisms create. Earth's plants reflect strongly in near-infrared wavelengths because of the cellular structure of leaves, producing a characteristic spectral signature called the red edge. Detecting this feature on an exoplanet would require direct imaging rather than transit observations, and remains beyond current capabilities for Earth-sized worlds, though future extremely large telescopes might achieve the necessary sensitivity. The challenge of detecting biosignatures increases dramatically with distance, because fainter signals require longer observation times to accumulate enough photons for reliable measurements. A potentially habitable planet 10 light-years away presents a much easier target than an identical world 100 light-years distant, not because the planet itself changes, but because its star appears fainter from Earth and provides fewer photons to analyze. This distance effect prioritizes studying nearby systems, where the brightest host stars allow the most detailed atmospheric characterization. Cloud cover on exoplanets complicates biosignature detection by obscuring the lower atmosphere where many gases concentrate and by altering the amount of light that filters through during transits. Thick, high-altitude clouds might prevent any light from passing through the bulk of the atmosphere, rendering transmission spectroscopy ineffective for characterizing the atmospheric composition below the cloud tops. Understanding cloud properties therefore becomes essential for interpreting observations and determining which atmospheric layers remain accessible to study. Retrieval algorithms, sophisticated computer codes that compare observed spectra to millions of theoretical models, allow astronomers to determine which combination of atmospheric gases, temperatures, and pressures best matches their data. These algorithms work backwards from the measured spectrum to infer the atmospheric conditions that must have produced it, accounting for factors like cloud cover, surface properties, and stellar contamination from star spots or flares. The results include uncertainty, estimates that reflect how well the models constrain each atmospheric parameter. Multiple observations using different instruments and techniques help confirm tentative biosignature detections and rule out false positives. If one telescope finds hints of oxygen in a planet's atmosphere, other observatories should attempt to verify that detection using independent methods and wavelength ranges. Consistency across multiple observation campaigns would strengthen confidence that the signal is real rather than an instrumental artifact or data analysis error. The philosophical implications of detecting biosignatures on an exoplanet would be staggering, even if we could learn nothing more about the organisms producing them. Confirming that life exists elsewhere in the universe would demonstrate that biology emerges wherever conditions allow rather than requiring a miracle. This knowledge would transform humanity's cosmic perspective and fuel efforts to understand how common life becomes and whether it inevitably produces intelligence and technology. Alternatively, exhaustively studying potentially habitable worlds and finding no biosignatures would suggest that either life is extraordinarily rare, requiring circumstances that seldom align, or that our search strategies miss most forms of life because they don't produce detectable atmospheric signatures. This outcome would force scientists to reconsider which biosignatures to search for, and whether we can recognize alien life that evolved under very different conditions from Earth's biology. The next decade of atmospheric characterization should begin answering these profound questions as James Webb Space Telescope, upcoming ground-based extremely large telescopes, and future space missions observe dozens of potentially habitable worlds. Each new observation either confirms that a planet possesses the atmospheric composition needed for life or rules out certain possibilities, gradually narrowing the list of most promising candidates for hosting active biospheres. Frank Drake formulated his famous equation in 1961 to estimate the number of communicating civilizations in our galaxy, multiplying together factors including the rate of star formation, the fraction of stars with planets, the number of potentially habitable worlds per system, the fraction where life actually emerges, and so on through the development of technological civilizations. Modern exoplanet discoveries have constrained several terms in this equation, with observational data rather than pure speculation, though significant uncertainties remain for the most crucial biological and sociological factors. The rate of star formation in the Milky Way, the first term in Drake's equation, has been estimated at roughly 3 solar masses per year, based on surveys of young stellar regions and measurements of the galaxy's total stellar mass. This star formation rate has varied over cosmic history, peaking when the galaxy was younger and declining gradually as the available gas gets depleted or ejected from the galactic disk. Understanding how star formation rates change over time helps predict how many planetary systems of different ages populate the galaxy. The fraction of stars hosting planetary systems, once completely unknown, now approaches certainty based on Kepler mission results and ground-based surveys. Statistical analyses suggest that essentially every star has planets, with typical systems containing multiple worlds rather than lone planets orbiting in isolation. This near ubiquity of planets means the galaxy contains hundreds of billions of planetary systems, providing vast numbers of potential sites where life might arise. The number of potentially habitable planets per system varies dramatically depending on the star's mass and age. Red dwarf stars with long lifetimes and close inhabitable zones might commonly host multiple planets at appropriate orbital distances, while massive hot stars evolve too quickly and have habitable zones, so distant that stable planetary orbits become difficult to maintain. Statistical extrapolations from Kepler data suggest that roughly 20% of Sun-like stars have Earth-sized planets in their habitable zones, implying billions of such worlds exist in the Milky Way alone. However, orbiting in the habitable zone guarantees neither that liquid water actually exists nor that life has emerged. Many factors beyond orbital distance influence habitability, from atmospheric composition to stellar activity to planetary mass and magnetic field strength. The fraction of habitable zone planets that actually possess the conditions needed to support life remains completely unconstrained observationally, though theoretical arguments suggest it could range from nearly all of them to an incredibly tiny percentage depending on how restrictive the necessary conditions truly are. The origin of life on Earth roughly 3.5 to 4 billion years ago provides our only empirical data point for estimating how readily biology emerges on suitable worlds. Some researchers argue that life appeared relatively quickly after Earth cooled enough to maintain liquid water, suggesting abiogenesis occurs readily when conditions permit. Others note that billions of years separate prokaryotes from eukaryotes, and billions more passed before multicellular life appeared, indicating major evolutionary transitions are rare and difficult. The frequency of intelligent life developing on planets that harbour simple organisms remains perhaps the greatest unknown in estimating communicating civilizations. Earth's billions of species include only one that has developed technology capable of modifying its planet globally and transmitting signals into space, suggesting intelligence might be rare. Alternatively, the 5 mass extinctions in Earth's history could have repeatedly reset evolution, and without these catastrophes, intelligence might have arisen much earlier. The average lifetime of technological civilizations that develop interstellar communication capabilities could range from centuries if most societies destroy themselves through warfare or environmental collapse, to millions of years if civilizations typically survive their dangerous adolescent phase and achieve stable long-term sustainability. This factor most sensitively determines whether we should expect to detect alien signals, since even common civilizations would be essentially invisible if they all perish shortly after developing the capacity to signal across light years. Combining modern estimates for each term in Drake's equation produces wildly varying results depending on assumptions about biological and sociological factors. Conservative estimates suggest our galaxy might contain only a handful of communicating civilizations at any given time, while optimistic scenarios predict millions of technological societies. Observational programs like SETI test these predictions by searching for artificial radio or optical signals, though decades of surveys have found no convincing candidates despite improving sensitivity. The Fermi paradox asks where these civilizations hide if they're common, noting that even slow spacecraft could colonize the entire galaxy in a few million years, a tiny fraction of cosmic history. The silence we observe could mean civilizations are rare, they don't expand into space, they exist but remain difficult to detect, or they've already visited Earth in our prehistory and left. Each potential resolution to the paradox carries profound implications for humanity's future and our prospects for surviving as a technological species. Habitable exoplanet discoveries inform these discussions by revealing how common Earth-like worlds truly are, and whether the circumstances that allowed life to emerge here occur frequently throughout the galaxy. If billions of potentially habitable planets exist, but detailed atmospheric studies find no biosignatures among the nearest examples, it would suggest life is rare despite suitable environments being common. Conversely, finding biosignatures on numerous worlds would indicate biology emerges readily and might commonly produce complex ecosystems that alter planetary atmospheres detectably. The answer to whether we're alone in the universe likely lies waiting on worlds orbiting nearby stars, written in the chemical composition of their atmospheres for any civilization advanced enough to read it. The current generation of astronomers stands poised to potentially answer this ancient question within their professional lifetimes through patient observation and sophisticated analysis of light filtered through alien skies billions of kilometers away. Reaching the nearest potentially habitable exoplanet presents engineering challenges that dwarf any technological achievement in human history, requiring us to solve problems in propulsion, life support, radiation shielding, and navigation that remain far beyond current capabilities. Proxima Centauri b, our closest exoplanetary neighbour, at 4.24 light-years, sits roughly 40 trillion kilometres from Earth. Voyager 1, humanity's fastest and most distant spacecraft, travels at about 61,000 kilometres per hour and would require over 70,000 years to cover that distance if it were headed in the right direction. Chemical rockets like those that launched the Apollo missions to the Moon cannot achieve the velocities needed for interstellar travel because they carry both fuel and oxidizer, limiting their maximum speed through the rocket equation that relates exhaust velocity to the ratio of initial to final mass. Even the most efficient chemical propulsion systems max out at velocities of perhaps 20 to 30 kilometers per second, roughly 1/10,000th the speed of light. Reaching even the nearest stars in human lifetimes requires velocities at least 1,000 times faster than chemical rockets can achieve. Nuclear pulse propulsion, first seriously studied in Project Orion during the 1950s and 60s, proposes using nuclear explosions detonated behind a massive pusher plate to accelerate spacecraft to high velocities. The concept is simple in principle, repeatedly exploding nuclear bombs and riding their shockwaves like a surfer rides ocean waves, gradually building up speed through thousands of precisely timed detonations. Theoretical studies suggest nuclear pulse propulsion could achieve velocities of 3 to 5% of light speed, allowing trips to nearby stars in roughly a century. Project Daedalus, designed by the British Interplanetary Society in the 1970s, proposed a two-stage fusion rocket that would use deuterium and helium-3 as fuel, triggering controlled fusion reactions to generate thrust. The spacecraft would mass 54,000 metric tons at launch, mostly fuel, and accelerate for 4 years, before coasting for 42 more years to reach Barnard's star at 12% of light speed. While purely theoretical, Daedalus demonstrated that fusion propulsion could enable interstellar missions within single human lifetimes. Though the engineering challenges remain formidable, antimatter propulsion offers theoretically higher performance than any other rocket concept, because matter-antimatter annihilation converts mass directly into energy with 100% efficiency, according to Einstein's famous equation E = mc². A spacecraft carrying antimatter fuel could achieve exhaust velocities approaching the speed of light, enabling missions to nearby stars in decades rather than centuries. However, producing and storing antimatter remains prohibitively expensive and technologically challenging, with current annual production measuring just nanograms, while interstellar missions would require tons. Breakthrough Starshot, announced in April 2016, proposes sending gram-scale spacecraft to Alpha Centauri at 20% of light speed using ground-based laser arrays to propel lightweight reflective sails. The concept sidesteps the rocket equation by leaving the power source on Earth rather than carrying fuel, using powerful laser beams to push ultra-thin light sails, accelerating them to relativistic velocities within minutes. Such probes would reach Proxima Centauri in about 20 years, transmitting data back to Earth 4 years later after the light travel time delay. Building the laser array for Starshot requires technology that doesn't exist yet, including a phased array of lasers delivering roughly 100 gigawatts of power, focused on a meter-scale sail millions of kilometers away. The sail must be just atoms thick to minimize mass, while remaining reflective and durable enough to survive both the intense laser bombardment during acceleration and collisions with interstellar dust during cruise. Developing materials with these properties challenges materials science at fundamental levels, requiring breakthroughs in carbon nanotubes, graphene, or entirely new materials. The information returned by such probes would be limited by the tiny mass budget that allows the high velocities Starshot requires. A chip-scale spacecraft can carry miniaturized cameras, processors and transmitters, but collecting detailed data about a planet's atmosphere, surface or potential life signs requires instruments that currently mass kilograms or tons. Trading off probe mass against mission duration represents a fundamental challenge, with heavier, more capable probes taking centuries to arrive while ultralight probes reach their targets quickly, but can only return basic reconnaissance data. Generation ships represent the classic science fiction solution to interstellar travel, building enormous spacecraft that sustain populations of thousands or millions through journeys lasting centuries or millennia. These mobile habitats would need to provide complete closed-loop life support, recycling air, water and nutrients indefinitely, while shielding inhabitants from cosmic radiation and maintaining social stability across dozens of generations. The engineering challenges are matched by sociological questions about how crew populations would govern themselves and stay motivated during voyages that outlast individual lifespans by factors of 10 or more. Suspended animation or cryogenic freezing could allow biological organisms to survive centuries-long voyages without consuming resources or aging, reducing life support requirements from supporting active populations to simply maintaining frozen tissues. However, successfully freezing and reviving humans remains beyond current medical technology, with ice crystal formation destroying cellular structures and current cryopreservation techniques requiring toxic chemicals that prevent ice formation. Achieving reversible suspended animation would revolutionize not just space travel, but medicine generally, allowing time for developing cures to currently terminal diseases. Relativistic time dilation offers another potential solution to the time problem by exploiting special relativity's prediction that moving clocks tick slower than stationary ones. A spacecraft travelling at 90% of light speed would experience time passing at roughly 44% the rate that Earth experiences, meaning a 40-year trip to Proxima Centauri measured on Earth would feel like only 17 years to the crew. Reaching such speeds requires astronomical amounts of energy and creates other problems like collisions with interstellar dust becoming catastrophic at relativistic velocities. The energy requirements for interstellar travel stagger the imagination, with even the most efficient propulsion systems requiring more power than human civilization currently produces. accelerating a 100-ton spacecraft to 10% of light speed requires kinetic energy, equivalent to hundreds of billions of tons of TNT, comparable to the world's entire nuclear arsenal. Generating and delivering this energy efficiently represents a fundamental challenge that likely requires fusion power, antimatter, or technologies we haven't yet conceived. Interstellar navigation presents subtle challenges because spacecraft travelling for decades or centuries must continuously update their trajectories to account for the motion of stars relative to each other. Stars orbit the galaxy at different speeds depending on their distances from the galactic centre, causing their relative positions to shift over time. A ship aimed at where Proxima Centauri appears today would miss by trillions of kilometres if it took centuries to arrive, requiring continuous course corrections throughout the journey. Communication with interstellar probes or colonies faces unavoidable light speed delays that increase with distance, making real-time control impossible and requiring spacecraft to operate autonomously. A message from Proxima Centauri takes 4.2 years to reach Earth, meaning any conversation involves minimum delays of 8.4 years between sending a question and receiving an answer. This delay grows linearly with distance, reaching decades or centuries for more distant target stars and fundamentally altering how interstellar missions must be conducted compared to solar system exploration. Radiation shielding for interstellar missions must protect crew or electronics from galactic cosmic rays, the high-energy particles that constantly bombard spacecraft in interstellar space. These cosmic rays penetrate deeply into materials and can damage biological tissue or electronics, causing cancer in living organisms and bit flips in computer memory. Spacecraft need either passive shielding using dense materials like water or active shielding using magnetic fields to deflect charged particles, both of which add substantial mass that reduces the maximum achievable velocity. The psychological challenges of interstellar travel may prove as formidable as the technological hurdles, with crew members facing isolation, confinement, and monotony during decades-long voyages through empty space. Studies of Antarctic research stations, submarines, and the International Space Station provide some insights into how people cope with isolation and confinement, but these analogues last months rather than years or decades. Maintaining mental health and social cohesion across multi-generational voyages requires careful crew selection, habitat design, and social structures that remain largely theoretical. Sample return missions from exoplanets represent an even more distant prospect than one-way reconnaissance, because round-trip missions double the distance and require carrying fuel to decelerate into orbit around the target star, explore it, then accelerate back toward Earth. A round trip to Proxima Centauri using current propulsion concepts would require hundreds of thousands of years, far exceeding any reasonable mission duration. Bringing back physical samples from potentially habitable worlds likely awaits technological breakthroughs we can't yet imagine, or requires accepting multi-century mission durations with spacecraft, returning to civilizations that have changed beyond recognition. In situ resource utilization, using materials found at the destination rather than bringing everything from Earth, could enable more ambitious missions by refueling spacecraft with locally produced propellant or building habitats from native materials. However, this requires knowing what resources exist at the destination and having the technology to extract and process them autonomously, both of which remain highly uncertain for exoplanetary systems we can barely characterize from Earth. Robotic precursor missions might survey target systems and establish resource extraction infrastructure before human crews arrive, though this approach multiplies the already enormous mission costs and durations. Self-replicating probes represent a speculative solution where spacecraft that reach target stars build copies of themselves using local materials, then send those copies to additional star systems in an exponentially expanding wave. Such von Neumann probes, named after mathematician John von Neumann who pioneered the theory of self-replicating machines, could in principle explore the entire galaxy within a few million years even using slow spacecraft. However, building machines sophisticated enough to reproduce themselves in completely alien environments using unknown materials remains far beyond current capabilities. The economics of interstellar travel present perhaps the most fundamental barrier, because the costs of developing the necessary technologies and launching missions likely exceed trillions of dollars, investments that dwarf current space budgets by orders of magnitude. No obvious economic return justifies such expenditures, leaving scientific curiosity and species survival as the only compelling motivations. Whether human civilization will ever develop the wealth and motivation to seriously pursue interstellar travel remains an open question that depends on unknowable future developments in technology, economics, and societal priorities. Despite these daunting challenges, serious researchers continue studying interstellar travel because the potential rewards include ensuring humanity's survival beyond Earth and answering profound questions about our place in the universe. Each technological advance in propulsion, energy generation, materials science, and life support brings interstellar capabilities slightly closer, even if the final breakthrough remains decades or centuries away. The nearest potentially habitable exoplanets wait in the darkness, and whether humanity will ever reach them depends on choices we make about technological development and long-term goals over the coming centuries. The search for habitable exoplanets has progressed from science fiction to observational science in less than 3 decades, transforming humanity's cosmic perspective from assuming planets rarely exist to recognizing that most stars host planetary systems. Astronomers have confirmed thousands of exoplanets orbiting distant stars, with dozens of those worlds positioned in habitable zones where liquid water might exist on their surfaces. Some of these planets share remarkable similarities with Earth in size, mass, and orbital distance from their stars, suggesting that the ingredients for life as we know it might be common throughout the galaxy. Proxima Centauri b orbits the nearest star system to Earth at just 4.2 light-years distance, though intense radiation from its active red dwarf host raises serious questions about whether the planet retains an atmosphere or has been stripped bare by stellar flares. The TRAPPIST-1 system offers 7 Earth-sized worlds, with 3 orbiting in the habitable zone, providing multiple opportunities for life to emerge if the planets manage to retain atmospheres despite their star's energetic outbursts. Kepler 452b circles a Sun-like star at an Earth-like distance, but receives excess energy from its aging host that might have already driven runaway greenhouse warming similar to Venus. Each potentially habitable world presents unique challenges and opportunities, from the crushing gravity and possible runaway greenhouse on Kepler 452c to the tidal locking and flare bombardment affecting Proxima Centauri b and the TRAPPIST-1 planets. Some candidates orbit quiet, stable stars but sit at large distances where temperatures might be too cold for liquid water without thick greenhouse atmospheres. Others receive perfect amounts of stellar energy but circle active flare stars that could sterilize their surfaces repeatedly over billions of years. The distance separating us from these worlds presents the ultimate barrier to detailed study, requiring remote observations that reveal only basic properties while leaving crucial questions about atmospheric composition and surface conditions unanswered. Current telescopes can detect Earth-sized planets and measure their masses and orbital parameters, but characterizing their atmospheres and searching for biosignatures remains challenging, even for the most favorable targets. Future observatories with larger mirrors and more sensitive instruments will gradually close this knowledge gap over coming decades. The search continues because understanding whether life exists beyond Earth ranks among the most profound questions humanity can ask, with implications spanning from practical concerns about our species' long-term survival to philosophical questions about consciousness, intelligence, and purpose. Finding definitive evidence of life on another world would demonstrate that the origin of life doesn't require miraculous luck, but can emerge from chemistry whenever conditions allow, suggesting the universe teems with organisms of every imaginable variety. Conversely, finding that potentially habitable worlds commonly lack biosignatures would indicate that either life's emergence requires extremely specific circumstances that seldom occur together, or that biology commonly arises but rarely survives long enough to alter planetary atmospheres detectably. This knowledge would inform estimates of how many intelligent civilizations exist in the galaxy, and whether we should expect to make contact with them eventually, or remain isolated in the cosmic wilderness. The habitable exoplanets we've discussed represent humanity's best current knowledge about where to search for life beyond Earth, though new discoveries and improved observations constantly update and refine that understanding. Some of today's most promising candidates may prove uninhabitable when examined in detail, while worlds we haven't discovered yet might turn out to be the true Earth analogues we've been seeking. The search continues because the potential rewards justify the effort invested. Understanding what makes planets habitable teaches us about the delicate balance that sustains life on Earth, and the various ways that balance can fail, from runaway greenhouses to atmospheric stripping to tidal locking extremes. This knowledge might help humanity avoid destabilizing our own planet's climate, while also preparing us to recognize habitable conditions on worlds very different from our own. A planet with a thick carbon dioxide atmosphere and permanent cloud cover might appear uninhabitable at first glance, yet support thriving ecosystems in niches where temperatures and pressures allow liquid water. The coming era of atmospheric characterization with James Webb Space Telescope and a future extremely large telescopes will begin answering questions about which potentially habitable worlds actually possess the atmospheres and chemistry that life requires. These observations will separate true candidates from false positives, revealing which worlds deserve the most intensive study and potential future exploration. Within your lifetimes, we may know whether life exists on planets orbiting nearby stars, fundamentally changing humanity's cosmic perspective. If you found this exploration of potentially habitable exoplanets fascinating, if learning about the worlds that might someday shelter humanity expanded your cosmic horizons, then show your support by hitting that like button and subscribing to this channel. Share this video with anyone who wonders about Earth's place in the universe and whether we're alone among the stars. The search for life beyond Earth continues, propelled by human curiosity and the profound questions about our origins and our future that drive us to explore the universe around us. These are the worlds that might replace Earth someday, distant refuges waiting in the darkness for humanity to develop the technology to reach them, and the quest to find them represents one of civilization's greatest scientific endeavors.